talk about a new lensing landscape in the year of time domain, multi-wavelength, multi-messenger astronomy. Thank you, Martin.
Thank you for the introduction. So this is what you read there is the abstract. So let's go to the title. Maybe it's more humble title. That's motivation. That's what we are doing now. What we are interested in doing. Okay, so this is the outline of the talk. I'll give a brief outline of what lensing is, although probably very well. I'll discuss briefly some transients from microlensing, then strong lensing of transients, then lensing about gravitational waves. Wave lensing, which is more newer side, and all this in the context of the future or upcoming wide field surveys. So, as you know, light propagates in blue geodesics. When we are in GR, small perturbations, this is how the metric looks like. And then we make this equal 0, and then we have propagation of light. So we can assign a sort of a refraction index to light propagation in a gravitational field, and we just go by the Fermat principle and find the solutions. I like to put it in this way to recall every time that if we are not in general relativity, then this field here will be different from these two. So there are two types, two scalar fields that govern the perturbations in a generic metric theory. So we can use this also to test modification of the differences on these two fields. I'll just briefly show one result on that. That's not the subject of this talk, but that has been a lot of subject of a lot of work from our group. So anyway, from this refraction index, we can compute the deflection angle of light. So if we have a spherically symmetric mass distribution, that's the angle deflection. Before GR, this was predicted also, but there was a factor of 2 difference. So really, deflection of light is a relativistic effect. So from this tiny effect of light deflection, there's a lot of phenomena. So if you think about the strength of the phenomena, there is a strong lensing which provides multiple images, very strong magnifications, time delays between the different images. These distortions can be in the form of arc or even rings. There is a weak effect that produces a very small twist in the shapes of the galaxies. This has to be measured statistically. We will not discuss this today. And with respect to the angular scale, we have scales which are on the micro arc second scales, which are basically within our galaxy, stars lensing stars or planets lensing stars. We have also lensing of quasars by stars in another galaxy. And then we have lensing by galaxies and clusters, which produce a microscopic effect in the sense that the shapes can be directly measured on images. So in these cases, we usually don't see the effects in an image, but we see in the light curve. So we see a change in magnification. So that's what we'll be concerned today in strong lensing and both in the macro lensing and micro lensing scales. Also, there has been new phenomena of lensing, which is the astrometric micro lensing for black hole shadows, you all know, retro lensing, temporal lensing, which I'll measure briefly, lensing of gravitational waves. So basically, lensing is everywhere, and it has been measured almost everywhere, from the scales of planets to the large scale structure of people. Okay, good. So let's start with microlensing. It's very simple. You have a source of light, some lens in between. They are moving, so the magnification changes. That's the magnification. So relative to, this is perpendicular, you are looking at this plane. The stars are moving relative to the lens, and this motion produces a light curve, a very characteristic light curve. So a variation of magnitude as a function of time. It's very rare to have a precise alignment of the stars, such as to produce these lights. So you have to look at many stars. But nowadays it's very easy. You have these large cameras, digitalized, of course. You can do everything in a computer, and you can start finding these lenses stars. So Einstein thought this was impossible. Now there are over 20,000 events of microlensing detected. Okay, and about 200 of them are made by planets. Okay, so that's a very typical characteristic single lens light curve. And of course, as I mentioned, there is also the microlensing of quasars by stars in a galaxy, which is already lensing. So you have multiple images of a quasar, and the individual stars or sets of stars in the galaxy are lensing these multiple images. So one of the big stars here is the upcoming Rubin Observatory, the legacy survey of space and time. That's a complete new telescope, very large mirror, very large camera, also very fast readout. So it's basically an instrument that can map the sky in a very fast and deep way. Also is a good resolution. So basically it's a deep project that will map the sky in the time domain. So there has been, of course, several surveys like the Dark Energy survey in which Brazil participates. This is, let's say, it's more like a static image of the universe. Here with LSST we have like a movie of the universe. So you can start looking at everything we did before in a better way, but also do new things in the time domain. So that's what we are willing to explore here in this talk. Just to have an idea, we expect to have about 1 million alerts of anything that varies in the sky per night. So we need brokers, and I'll mention briefly what are brokers. And the survey is about to start, actually. So start towards the end of this year, and science operations next year. The way that this thing is managed in the scientific aspect, there are 8 science collaborations. So each one focuses on different science aspects. And what I'm participating in is the transients and variable stars, which is a collaboration that deals with, among other things, microlensing, the strong lensing science collaboration, the name already tells, and the dark energy science collaboration, which has everything that's involved with dark energy and dark matter, by the way, including gravitational lensing as well. So Argentina and Brazil, they are both members of LSST due to in-kind contributions. Chile is a member because the telescope is in Chile, so any Chilean has access to this telescope. So it's a truly Latin American, South American collaboration, and I think that fits very well with the ICTP and SAIFR.
And Mexico.
And Mexico is also part of it. Yes, thanks. As we said that there's 1 million transients per night. So we are interested in finding only the microlensing events. How can we separate from all of them? You have lots of data. We are looking for patterns. So as you heard from Raul, the way of going to this is, of course, machine learning. So why are we looking for these microlensing events? There are many interesting reasons. LSST is like the truly first all-sky survey for microlensing. There have been other surveys of microlensing looking at the bulbs, so mostly for planets, or looking at the magnetic clouds, mostly for dark matter. But it's like full sky microlensing. So we have information about compact objects in different directions of the sky that we didn't have before. We'll have a census of compact objects in general, and of course we'll find planets. But we want to decide whether some light curve is a microlensing event or any other thing that varies. And also we want to be able to follow up these things, because it's important to break the general system, for example, to get spectroscopy of the source. It's important to have a denser time light curve. If you want to look for planets, you want to observe more frequently than what LSST does. So we do want to rapidly understand that that's a real microlensing event and follow. And the structure that do these kind of things are known as brokers. So this is not part of LSST, it's like an independent thing. There are 7 brokers for LSST, and what the brokers do basically is to collect information from LSST on other sources, classify this, and send alerts for specific systems, for example, microlensing. So there is the microlensing observation platform, MOB, that's connected to a broker, and is I'll talk about that more later, but it's what will control a network of telescopes for the follow-up of microlensing events. But also after LSST has this 10-year period, we have many events that we were not able to follow up that we can just study the light curves. So either for real time or for afterwards, we want to be able to identify the systems. So one classifier that we have been using is the microLEA machine learning classifier. That's kind of a old-style machine learning in the sense that it uses features and uses random forests or fully connected neural networks. But also with the group at CPF, we've been working with the recurrent networks that are more flexible and very well suited for this kind of events. To train, of course, machine learning is all about training. We have to have realistic training sets, and for that, we have been using challenges that were produced by LSST, like Elastic and Class. But these are not enough for our purposes, so we add our simulated light curves, both microlensing events, as well as other variable stars that are not there. and we are porting what we are doing also to the Think broker. In Think, it uses LSFT simulated data, but also it uses real data from the Zwicky transient facility. So that's the kind of confusion matrix that we get using the elastic and plastic. These are different categories of variable things, mostly variable stars. This is microlensing. So we are able to recover about 99.8 of the microlensing effects in these studies. Okay, so in what regards microlensing, there will be another infrastructure which is Roman Space Telescope that it's half for cosmology and half for other things. And one of these half is to look at the bulb to discover planets, both for transients and using microlensing. So Roman has a survey in the bulge, and it will be observing the same time that Rubin is observing. So we are exploring these concomitant observations. The main interest here is planets, especially free-floating planets, which is basically the only way to discover these free-floating planets. Apparently, there is one free-floating planet, more than one free-floating planet per star, the galaxy. So that's a lot. Of course, we are simulating these three categories of lenses, binary lenses, also black holes. So we produce these simulations of light curves, basically putting all we know about Roman observations, all we know about the Rubin observations, and we produce these simulated light curves. Blue is Roman, and the colorful are different bands of LSST. And then we fit these light curves as we would fit real light curves to see the information we can extract from them. So basically, we are making the case for this joint coordination of these two surveys. What Rubin can do is to provide a baseline for Roman. For example, here Roman is doing observations only on the peak, but Rubin can provide this longer baseline, which is important. Also, it can fill the gaps, like here, of Roman. And also, due to the different points of view, since Roman is in L2 and we are observing from the Earth, there is a difference in the light curves, which is the parallax. And measuring the parallax have to break a lot of genetics, so that's something we want to do. If we can. Okay, that was microlensing. So now let's switch to macrolensing. So multiple images, like here, Einstein ring, multiple images of a quasar. So if these quasars have variability, each of these images, they will have a similar light curve but shifted by some time delay. And the time delay is very sensitive to the Hubble constant. So there is this problem that Raul was mentioning that high redshift and low redshift measurements of H0, they don't agree. Well, this is a very complementary way of measuring the expansion rate, which had subject to totally different systematics than the other methods. So people are willing to improve this a lot. For now, there's a bunch like 10 systems that use to measure that. And this will improve by order of magnitude with LSST. But also, quasars have this complicated light curve. If we have instead of quasars, supernovae, so multiple image supernovae, which have working for simple light curves, then also we can calibrate the light curves themselves. So we can not only measure the time delays, but we can also account for the different fluxes using strong lensing. But we can also measure the intrinsic magnitude of the supernova. So there's a lot, it's like a holy grail. There's a lot of information that we can take from this system. Up to now, there's about 3 in the galaxy scale, about 3 multiple image supernova. So Rubin expects to discover about 100 with Roman 40. So that's the redshift distribution. And also, this supernova could be a kilonova too. So this may be also sources of information on multi-wavelength objects or multi-messenger. Okay, so that was that. So looking for strongly lensed transients or strongly lensed variable things are very resourceful for cosmology. Now let's forget the optical. Let's think about gravitational waves. Gravitational waves can also be strongly lensed. They have, by the way, the propagation of these waves in the gravitational field is the same. So basically, strong lensing equations are the same. So there is basically 2 regimes. One where you have supernova from one direction, kilonova or anything, just a merger of binary black holes. Some gravitational waves coming from one direction. You have a multiple image of it, but it comes at different time. come at a different time because of time delays. So you have something like this, like a string is like this. You have two in different times, two signals of the coalescence of a binary something, and they have different magnifications and they will have different time delays. And also, if the lens is not something big as a galaxy or galaxy cluster, but it's maybe a very massive star or black hole, the lens, then you have like a superposition of these things, and you have a beating part pattern. Okay. Okay, so we expect that eventually we'll find strongly lensed gravitational waves. So, okay, if I know the time delays, I have multiple Newton lens. If I see a lens over there, then of course we can do a lot of things. In general, the localization of gravitational waves is not very good, so we know very broadly where the gravitational wave is coming from. But if we measure the time delays and the magnifications, then we know there is a lens over some field, let's say even over 50 square degrees. Let's say you have 500 lenses, but if they match the time delay and the magnification, you know from which lens this gravitational wave is coming, from which direction it's coming. So you can really localize even like a dark, even if the gravitational wave doesn't have an optical counterpart, you can localize it. So that's very nice for dark standard science. Okay, so it's to do this science, it's very good to have a lookup table. As I mentioned, in the case of gravitational waves, if you don't have an optical counterpart, you need to have mapped where the strong lenses are, and also what their magnifications are and what the time delays are. Or even LSST will find strong lens because the image is served, right? But at the beginning, it will be mapping the sky. At some point, you run our finders. But if you just find a triangle somewhere before you know that there are strong lenses, what do? If you already have a combination of strong lenses where they are, and you know there is something viable there, you can match them and say, well, that's a strongly lensed event, or whatever. Also, if you have other surveys like the 3D transit facility ongoing now, it doesn't have very good image quality, so you cannot find lenses. But if you know there is a viable object that's repeating or that's multiple, and you know that's a strong lens there, you can use this information. So that's something we are doing. So we are cross-matching our strong lensing catalogs with supernova found on CPF, and we found many matches. We are looking. Okay, so if you have a combination of strong lenses, that's already useful. But if you have a modeling of these lenses with the predictions of the magnifications and the time delays, that's like very useful. We can look at repeating signals about everything. Gamma ray bursts, fast radio bursts, gravitational wave, whatever. If there is you don't need a very good localization because we don't have so much strong lensing in the sky. That's one point. So that's a very sparse system. They are rare. In that case, it's good because the fact that they are rare means that we can localize things that are not very localized by other means. Okay, that's it. So to build a very large set of strong lenses, to build lookup tables for all these applications, what we did is to get a lot of strong lensing catalogs, combine many strong lensing candidates, and then look at the very wide surveys that are available nowadays. The wide field surveys that have good image quality, like DBS, CS82, and many. And we just started making catalogs, images of the system, also cross-matching with photometric catalogs like SDSS and with spectroscopic catalogs to build these value-added, large strong lensing data sets to be used as a lookup table. So basically, that's the sky coverage. Each dot here is one strong lensing system, and these are the footprints of the many surveys. When you see names here, are the students involved in these works. So we have about 300,000 images because, well, that doesn't mean we have 300 systems, but we have different bands, different surveys. Okay, so that's some combination of some systems. They are basically mostly on galaxy scale. Okay. So there is an infrastructure called FLCOM, which is a database that you can query, you can feed information in, and you can keep this up to date. And the version we have built is just prior to Rubin, so we call this the last step before Rubin. Last Peru, we can make many things about, but there's no time to go with his name. And so the going work with this sample, on the one hand, this is just a compilation. This is very heterogeneous. Some are just candidates. Now we are using manual visual inspection on all these systems using the Zooniverse infrastructure. First, we are doing a vetting, so it's classifying if it's strong lensing or not. And then in the second phase, we are doing a tagging. So is it galaxy scale, cluster scale, arcs, these are multiple quasars, whatever. And so at the end, we'll have a very large set of tagged systems that we will use our tags to model the systems. But we can also use this for machine learning applications and just train on real data, for example, classifiers, regression, and so on. So there is already massive modeling going on this database. There are over 150 systems that were modeled from strong lensing. We are working on the time delay predictions of them. We have a few just ready now. That's already the largest sample model so far. And this making time delay predictions as far as we know is a new one. Okay, that's João is doing that. I will skip the modified gravity part because not the main thing. You can ask questions. And just that we go from this 1 minute I have to the last topic, which is everything we said about lensing is the geometric optics limits. But the light is away, and when the short radius of the lens is on the order of the wavelength of light, then you start having wave optics behavior. If so, this thing is the ratio between the short radius and the wavelength. So if the wavelength is larger than the short radius, there's no lens. But if it's comparable or larger, then you have this kind of oscillations in magnification, which is like an interference pattern of multiple images. And this can have an imprint on the spectrum. So let's say it's the spectrum of a galaxy. Let's say that you are in this oscillatory regime. This is what you see as the spectrum. So there's a very clear pattern, and we look at, can we find this pattern in real data? And in which situations will we be able to find them? So we sort of look at a different wavelength. Of course, different ranges of wavelength have different ranges of mass. So for the very low masses, we are interested like in primordial black holes, light primordial black holes, have to look at gamma rays. If you have stars or planets, then you can look at radio and so on. So you can, depending on the mass of the lens, you can look at different frequencies. There are finite source effects that break this coherence, so you lose this effect. So there's another constraint that we have to account for the size of the source. But when we fold everything in, there are certain regimes, so certain mass ranges, certain distance ranges, certain size ranges. We depend on the lens and on the source, where we may be able to find wavelengths. We are calling this wavelengths. So just to recap, on the side of transients, there is micro lensing, there is strong lensing but with time delays. We are doing up this producing this lookup table. There are a lot of challenges to make follow-ups. We are carrying a pilot program at Casdeo, a telescope in Argentina, for the follow-up of microlensing events that starts next month. Transit time needs brokers. We are involved in the Sync broker, and connected to that, we are building a new camera for the Casdeo telescope that will be ready this semester. Multi-messenger, as we said, having multiple images of a strong gravitational wave event. They allow us to localize these events. We expect not that much in advanced LIGO, maybe one, but in Einstein telescope, we expect about 100 of these strongly lensed gravitational waves. Multi-wavelengths is something we're seeking to detect. Wave lensing is something we are seeking to detect. And that involves certainly the combination of multiple wavelengths observation. Sorry, these are.
Impressive, more than 12,000 strong lens.
Yes.
So we have enough time for a question. So,
one question. So the double signal bring down of gravity waves that you showed where you swung the waves against the dark side. So the one that you showed there is, I guess, for like a solar mass scale lens, very small lens, right? Because it's very so close together. Because otherwise, you're talking about months apart, right? Yeah. So so the question is that so then the lens can be, in that case, galaxies or something. So when the cases of a ring down which is close together, do you actually expect to see any optical or similar strong system? I find it hard to understand how you could see something in there that could be considered a counterpart. Whereas on the other, like you're talking about nice integrators of nothing phases, right?
So it's like the wave optics thing we discussed before. So if the wavelength of the gravitational wave, which is really large, is larger than the traction radius, you won't see any length. So in the wavelength that we see with LIGO, you will not see any effect by a star. Just it will not change the pattern. Okay. If you go to larger mass stars, like 200 solar mass or something, then you see this beating pattern, like the superposition of two oscillations.
Sorry, I was talking about the wavelength. I was talking about the strong wavelength.
Yes, that's what we also call that wavelength.
You also call this wavelength?
Yes. That's a nomenclature. Everything that's a blending, manifesting in a wave. So wavelength. We are calling strong lensing of gravity waves, wavelengthing as well as in the optical. Okay.
All right.
But I mean, as the equations are the same, it's the same phenomenon. So again, if in LIGO, a single star will not make any pattern. A galaxy or a cluster will make very separated curves. Like a supermassive black hole will do something like the plot I have shown, and a 200, say, star, 200 solar mass star, will make this beating pattern. It's very characteristic.
So what you show there is probably something like that.
Like supermassive black hole. Yes.
And that's so cool. I mean, that in scale that you show there is maybe a couple seconds.
Yes, it's very short. This was like illustration.
Yeah, I just wanted to see the region where you expect to see this.
Yes. But the time delays in the galaxies, as you say, it's weeks. Thank you, Martin.
Next speaker is Reula from University of Córdoba, professor at University of Córdoba, and he's going to talk about what they're doing in Córdoba. Yeah, very nice. I don't want to talk about.
This one? Oh, okay, sorry. I don't know which version.
Version of Sam.
The one that's that one. Okay, so I decided to spend my time talking about what we do in Córdoba, since we are talking about physics in South America, so I decided what we do in Córdoba and what we can whatever in the future. So we have a large group in general relativity about the researchers. Yeah, this is our version. I don't know what it was here. 5 students at the moment, several independent research lines. But I'm going to talk only about my part, because when I had 20 minutes, there was so I'm going to talk work with these 6 guys here. These are former students of mine: Federico Carrasco, Fernando Alvarez, Marcelo Rubio. He's back in Córdoba, he's in Mallorca, Sisa, and these are my recent students: Pablo Montes, Robin Pele, so the works are. I went to work in several labs. So I'm going to talk about particularly these months here. So we work since several years on those years around black holes. So the different starts with Carrasco, basically, and now we're working with this is done. It's a code, it's an American code. do a force-free release plasma fields around black holes or neutron stars. I will have code, very code. And recently we added this skyline code, which is supposed to be able to follow through the geometry of geodesics and see how we detect the satellites in space. I'm going to show you some examples. This hyperbolic system is a program that we have been running for several years now, which is understanding the hyperbolic systems. Mathematics, we understand hyperbolic systems. Physics, we have hyperbolic system with times of gauge, and there is no theory of matter theory that compresses bases at all. If we want to understand, fully understand scales, so we have done several advances. Then we are going to talk about the secret of these fluids, particularly conformal invariant fluids, which are very high conditions. And here we did some project, analytical project, describing on the conformal invariant fluids versus high problems. Then we did some numerical problems. And finally, with the Reula and a student, we're working solving numerical stationary equation. For that, we mean some region outside some star or some region, or having two black holes and which in this case we are not going to be solving the stationary equation because there is a solution. Once we can solve Ricci equal to something, then we can use some other equations and solve them. System minimal energy, etc. Rotating stars, etc. So and here the main point is being able to solve Ricci equation. So this is the force-free code to deal with the spheres. It's a code that has many patches. This particular here you have 6, many piles of these 6 patches, many. And so you solve for the region where you put boundary conditions here, boundary side. So you can imagine usually we put in the interior. Okay, in the interior, we can say, okay, this is the part of the hole, horizon, and the exterior is some region. With this code, we can simulate jets. And this is a jet, it's a parallel jet coming from putting boundary conditions here that is magnetic field. Trying to create some application distance outside. And this one is a black hole entering region with the Córdoba. So see that jets creates a jet. So in the case of pulsars, we have these are aniline pulsars, so the for moments in the same direction of the rotation. This is
notice that you create this region where you have connected lines into the star. In this case, this is a black hole. This is a binary system of a black hole. And so our aim was then to study what happens here. This region is also a region of the star for currents. Here also we have this current. So this is how it's on, so we have to develop this skyline code to get from here and observe satellite. In this case, it was so this was supposed to be a movie, but since there is a PDF movie, but basically how here to black holes with their accretion disk. This is a code that we wrote in Julia and Python. Now we are porting the full code to Julia. So before we did the start of the, so they create all the initial data for the geodesic propagation in Python, to the propagation in Julia faster, and then analyze the results after the propagation Python, but now we are happy with Python. So that's also very well practicing. And there is a package in Julia which is scaling skyline.ga. The trajectories are integrated useful. And you can provide geometries in terms of a lead and an integral geometry, or you can provide support. Solving some numerical code, so there is a nice support and it's free, so I go there. This with this code, one thing we did was look at the pulsar X-ray emission. Here you have the upper one, you have the computation of pulsars emission. This is the current, this is the charge. In the case of where you do it in flat space without any jump, that's plasma. And this is the same computation, but in curved space-time. And you see here, there are not too many differences, but here is there is a crucial one. Here you see that it's not current is not here, but here is 100%. So this touches some part of here, what you see here. This line is absent. So we try to use the code to get some pulsar like cards and compare with the observations. And here we have four that were very difficult to reproduce without this line here. People to reproduce these equations, people have to use either some quadrupole or some dipole that was not sent. Yes. Here we can do it. We don't know whether this is the right explanation, but we can do it quite well. Except this one is not so good because this one is very hard. For instance, here you see same like curves and the contribution from the main hotspot in the top near the poles, and these the green lines are the contributions from the other sort of source of view. See that they are quite important to the lines. Now we are working with this code also to get the gamma ray emission, which is the awakening. And we are also looking at the better atmosphere models for this, because this, although we can reproduce pretty well the light curves, spectra and so on. Model from the atmosphere. And we are also working in the binaries, the binary systems I showed you before. So that also like systems. So this was the part in astrophysics to come to this hyperbolic system. But hyperbolic system here we meant a system where you have some, you can think of this as a length. This is space-time index, so it's derivative of some fields and like parametric source, and this K and the J can be U. So this is what we call a first order hyperbolic system. Sometimes it's hyperbolic, sometimes it's not. And as I mentioned in the literature, you can have a theory we tell you is this metric has a property, this K metric has a property, then the system is hyperbolic and it's supposed to go to the machine and you can go and solutions. Change the vision data for this equation, the solutions change. So this is for instance, fluid dynamics. So, but in general, for instance, physics, we always have some problems where you have a constraints for gauge. For instance, mountains have EMB, but the versus B versus charge, magnetic dynamics, TR, etc. You have a system which have constraints and have gauges. So in the constraint case, we are working in both the constraints is finished now, so the gauge but we understand very well. For the constraint case, you get this system and say, okay, these are more equations than fields, so you have to reduce them, and this you call this a reduction that will bring you this metric that was rectangular to a square metric. And then you say you fit this system to this edge. And this is the system mathematicians can do. So this is one way of dealing with that, so that you reduce the equations. And the other way you do it, you increase the number of fields with more fields. This will be in case of, for instance, electromagnetism. You say, okay, I will take this equation, E dot equal to something, E dot equal to something, forget the constraints. You have this system. This system is kind of what you do when you do divergence scaling, for instance. When you add some equation for the divergence field, some other phi, which is phi dot is the divergence field. So you increase by 5 the size of the system, and there you get rid of the constraints and you solve a bigger system. And this has the advantage that if you have a constraint violation, then this constraint violation can be handled and then obtained at this time. So there are two schemes for that. So what we find was a necessary and sufficient condition to admit a hyperbolization. That means that you get this method K that will on the edge of the C, and you say, okay, this method K has a property, and if there is an edge, you can put there, and your system is well hyperbolic, okay, or there is a C which will make the system hyperbolic force. So either you reduce or enlarge, and you get the guarantee of the system. So this is the fourth constraint. And we have a generic way of extending the system. So this way would be how to find the edge, and this is how to find the extension C. And we have a generic way of finding extension. This is your system. Get the electromagnetism, vector potential, you add another equation for this equation. So this is a unique way or preferred way of extending the system to make sure that the system is. So, in dissipative relative fluids, what we are trying to do is these fluids are some really the generalization of fluids. That include dissipation, but we don't want to have a dissipation as a parabolic system, but that has infinite propagation speeds. So it's so what we ask is to have some system that has an entropy growth. In particular, we look at this with of the divergence type, which is data version the former studies of this. And we are looking in particular for formally varying. And the result we have is that there exists a unique 4-parameter family. So there is a one extra sound speed of 3 that there is just one. The other parameters are usually parameters for the branch dissipation. And we have then done some numerical simulations. So here, these numerical simulations are very interesting and very hard to do because you have two pieces of system. You have a conservative way of doing the system. That is, you need to have a shock probability. And you have some variables which are variables in which the theory is split down, and so you have to go always between these two system variables, and the way to translate from one to the other is not you need to go to it's not direct, but to go to every time very kind
I have a question about the pulsar X-ray issue.
Yeah.
Because you have the scope, but for the many parameters like the magnetic field or density, how do you have to fit the data?
Yeah, you have for the simulation you have the magnetic field, but in that case, so you can think of magnetic field or temperature, space, and then you have the compartments, star,
That's about it. So I have 2 parameters and then you see those.
yeah, you have to do a model for the most space, which is common when you are in the temperature. So, there is no more an inclination for, but there are few parameters. The guys is I don't know why we are doing it very well, but just for this together.
More questions? So if not, let's thanks all the speakers for their things. Then we have the meeting. Sorry. Very tight schedule. Their share is going to be their share. But
Oh, okay.
Not connected.
Yes, from Michael.
Sì, sì.
Eu concordo com você.
Brasil só perde para Manaus.
Mas no lugar de fazer isso não é assim, né?
So now we have Riccardo Sturani from Reula, from the beach side. So Riccardo will tell us about gravitational waves.
Okay. Thank you. Thank you for being here. So I'll give an overview of the observational situation. So what we've seen so far in gravitational waves. So there is nothing terribly new, actually. You might have heard this already, but just to give you the setup. Okay, how the experiment made, what are the observation we have so far, what are the data, what we get from them, and above all, how well do we need to know the waveform that is motivate the fact that there is a lot of work needed to do in the next 5-10 years to improve our modeling of the two-body problem, because binary systems are the prototypical and the only kind of sources we've seen so far. Okay, let's start with the experiment. How it is, how the experimental device is made. Yes, so it's it's a complication of the Michelson experiment. So there is a laser going back, a laser, not like this because it's infrared. It's going back and forth in the two arms. Sorry, this is the laser source. It's going back and forth in the two arms. So if the mirror moves because of presence of gravitational wave, then the interference pattern changes. So the intensity of light changes. So the output of the detector is a number for any instant of time. It's the intensity of light, whose variation is an indication of the variation of the light travel time, the difference of the light travel times in the two arms. So one important thing is that since only light travel time difference is measured, so if there is a gravitational wave affecting symmetrically the two arms, then the experiment is blind. So basically there are 4 directions the experiment is blind to it. So the real experiment is the sophistication of this because there are Fabry cavities. So light goes back and forth 500 times in each arm. So the minimal phase shift that current technology allow to measure is 10 to the minus 8. So the current phase shift used the wavelength of light, which is of the order of 900 nanometers of micron. That corresponds to the optical path 10 to the minus 15 meters divided by the number of bounces. So 10 to the minus 15 meters is the size of an atom. So this is the typical sensitivity. So it's more than the size of the nucleon of an atom. Of course, this is not because this device is capable of measuring the position of individual nuclei of atom, but measure the average position of a macroscopic size of the mirror. So, and there are many sources of noise. So you probably cannot read this, but the unit for noise is square root of hertz. And the reason for this funny unit is because you take the output of the detector, you imagine this in dimensional units. So the noise, the Fourier transform is unit of time. And you cannot really assess the quality of the detector by taking the Fourier transform of the output because the amplitude of the Fourier transform depends on the size of your chunk. So what is really a good figure of merit if your detector is the spectral noise sensitivity, which is this square root of the square of the spectral noise divided by the sampling in Fourier space. So this object is really the figure of merit of your detector, not the Fourier transform of the noise. And so the spectral noise, you can figure out then it has a dimension of unit of inverse of time. And so this is quadratic in the noise, so it's square root, it's the real figure of sensitivity. And to get an idea what is the best frequency that an interferometer will get, well, you have to think of wavelength of a gravitational wave arriving and being slightly larger than the size of your interferometer, because if it's smaller, yeah, more than one cycle over the size of the interferometer, so then the effect partially cancel. If it's longer, then you can expect that the signal is maximized. So you really need at least half of the wavelength of the gravitational wave being larger than the size of the interferometer. If the wavelength is too long, then the frequency is too low, then you are hitting into specific noise, which is basically seismic noise. You cannot hold the mirror stable on a scale of more than a second, basically, just because you have a lot of vibration of the soil, cars passing by the detector, people walking around, the sea waves hitting at the coastline tens of kilometers away from your hub, people chopping in the wood next to the hub. So basically below 10 hertz, below 15 hertz, forget anything. So that gives you that you cannot see arbitrary long wavelength. You cannot see arbitrary short wavelength because then short wavelength starts canceling the signal inside the detector. So the really best sensitivity is for the size of the detector that are in use is really around 100 hertz, 150 hertz, 200 hertz. Of course, the size of the detector is not hundreds of kilometers, it's only 3-4 kilometers. But as I told you, there are a few bounces, hundreds of bounces. That's why the typical size of order of hundreds to thousands of kilometers. Okay, and then just to summarize this idea that it's almost isotropic detector, but there is some modulation. You see the detectors are located in the US in Louisiana, in US in Washington, and in Italy. So for a wave arriving right above from the detector right below, then you have maximum sensitivity. If the wave arrives in one of those 4 directions that bisect the detector, those are the blind direction because they affect the 2 arms symmetrically. So the intensity of the combined line is not affected by a gravitational wave that affects symmetrically the 2 arms. So those are blind spots, and all the direction in between, they have some continuous variation. So optimal detection, optimal sensitivity to waves coming from above or below, 0 sensitivity from 4 specific directions, and then intermediate situation for all the other directions. So the 2 LIGOs, the detector in Washington State, no, not Washington DC, Washington State next to Canada, the detector in Louisiana, they are oriented in such a way that they have roughly the same response. The detector in Italy is oriented in a different way. That tells you that it's much more likely to have coincident detection between the 2 LIGOs rather than the third detector that is in Italy. Okay, this is almost all for the experimental apparatus. Let's go to the observations. So there was a first observation run that ran for 3 months. Of course, not all of the 3 months the detector were actually on. So basically half of the time is really the time, half of the length of the run is really, after the duration of the run is really when the detectors are actually sensitive. That was the second observation run. The first one was historical for obvious reason because saw the first detection ever in September 15. Then the second observation run was historic because it observed the double neutron star that had that was the first and up to now the only event with optical counterpart. Then there was a third observation run split into 2 periods of roughly 6 months each that basically detected most of the events. Up to now we have 90, almost 100, 90 confirmed events. Then O4A is actually not really ongoing. O4, the 4th observation run, started in May. It stopped 1 month ago. So the first half of O4 is over. The second half of the 4th observation run we start in 5 weeks. So at the end of March, we'll have the second chunk of the 4th observation run that will go on until the end of this 2024 year. There is Kagra, the Japanese detector that is located here and it's underground, has sort of already joined the collaboration, but it cannot take yet astrophysically meaningful data because the sensitivity is small, but that's completely natural. It's not that as soon as you turn on the detector that you immediately see something. You have to make a lot of hunting. It might take a few months more. And let's go to the actual data. So basically, this is the summary of the data. If you want to summarize in one slide, in one drawing, the results of the detection, this is. So these are the 90 detections. So each detection corresponds to 3 compact objects, 2 before the merger and 1 after the merger. So you see for each detection, there are 2 and 1. So by blue dots, by blue circles are meant black holes. The red ones are meant neutron star. How do we distinguish between neutron star and black holes? Well, by the mass. So whatever which is light enough, it should be a neutron star, because we know that stars imploding can give rise to either neutron star, well, can give rise even to white dwarf and objects which are less massive. But the object meaningful LIGO are neutron star and black holes. Why? Because they have to be compact. Okay, I mean the Earth going around the sun also emits gravitational waves, but you know the Earth is fat, so it means an orbit which is few thousand kilometers wide at least. Of course, the orbit of the Earth is 150 million kilometers, but the orbit of a fat body must be at least the size of the body. And so, since the detector is limited in the low frequency by 10 Earths, only very compact object, only object whose dimension is of the order of hundreds of kilometers at most, can give a signal which is in the band of LIGO. So all the objects that we see and we can dream of seeing are compact objects, neutron star and black holes, with this detector that are limited at low frequency. And we know by the theory of stellar collapse that you cannot have basic black holes for mass below 5 supermasses. And we know that equation of state of nuclear matter that we know they can sustain neutron stars only between 1.2 and 2. So whatever we observe in the range of 1 to 2 solar masses, we call it a neutron star, and whatever we observe between 5 and more, we call it a black hole. So there are a few intriguing objects. Of course, the result of a merger, which is in the region of 2-3 solar masses, well, it can well be a black hole and avoid the bound of stellar collapse, because it's a black hole that wasn't formed by stellar collapse. So we know for sure that now there are black holes of 3 solar masses that didn't come from stellar collapse. They came from merger, and that's perfectly fine. There is one very mysterious object here. It's a compact object because we saw it in LIGO, and we saw that its mass was 2.6-ish, and that's really at the limit of what equation of state of neutron star can allow for neutron star. So this is a sort of problematic object, or if you like, interesting object. It's probably something different than anything else we've seen. So, and then the top mass, we cannot go beyond 100 solar masses, because again, then you get too big the object, then the orbit has to be too large, and then the frequency goes too low, goes out of the LIGO band. So really, LIGO, Virgo, they really detect what are called stellar compact objects. What about black holes in the order of few hundred, 1,000, 10,000 solar masses? Do they exist? Probably yes. We don't know because we haven't seen them. I mean, there is this desert in observation of black holes in the mass of 100, 1,000, 10,000 solar masses, because we know that supermassive black holes exist. We have one in our galaxy. So according to what we know, almost all the galaxies have in their center a supermassive black hole, ranging from 10 to the 5 to 10 to the 9 solar masses. Those are really the center. And so clearly, supermassive black holes, they don't come from stellar collapse, but they are creating during the history of the galaxy. So there's something different. So we know there are solar massive black holes. So we see them with gravitational wave. I mean, we see black holes even electromagnetically in the near to us, but these are really extragalactic solar massive black holes. What happens to intermediate massive black holes, few hundred, 1,000, 10,000, that's a big mystery. And I will tell you, in the future, we might know about it. And about sky localization that it was mentioned. So the time localization of this system is very good, because basically the gravitational wave arrives, it changes the intensity of the recombined light of the laser. So basically, your time localization is limited by the number of photons. You cannot decrease too much the time localization, just because if you want to sample the signal of the laser to short time, then just don't have enough photon. And you cannot increase the intensity of the laser too much, because then you start heating the mirror and you start deforming the surface of the mirror, and then spoils your sensitivity. But apart from this fact, the time localization of the signal is very order of milliseconds. Sky localization, no. Sky localization is quite bad compared to electromagnetic, because you need triangulation. You need triangulation, so you need at least 3 detectors. If you have 2 detectors, you get a circle in the sky. And the circle in the sky is actually this double banana. So this double banana is never complete, it's never a complete circle, because eventually you will cross the blind region, the region to which you're blind. So whenever you see this kind of double branched sky localization, there was a sky localization by 2 detectors. Whenever you see a small region like this, there was a sky localization by 3 detectors that can really into a very small area, the sky. What about the third space-time as 4 dimension? I told you about time localization. I told you about angle localization. There is still distance. 5 minutes to go. Oh, okay. The sky localization, the distance localization, they are all system extragalactic, and we can see them up to the gigaparsec. That means that the systems in each galaxy are very rare, but since we're sensitive to objects well beyond our galaxy, then we can have a rate of, say, 90 events overall of 1 year of data. So okay, this is about the rate. So this is the rate. The units are per megaparsec cube per year. You know, the galaxy distance on average is of 6 megaparsec. So 1 megaparsec cube, there is 10 to the minus 2 galaxies on average. So this is the rate that we get per year, per megaparsec cube, we get from 10 to the minus 6 to 10 to the minus 8. That means that there is less than one event per mega year per galaxy. Okay, if you're just looking at one galaxy, then you should expect less than one event, 0.1 event, 0.01 event per mega year, per million year, per galaxy. But since we are sensitive to up to gigaparsecs, then we can integrate over many galaxies, over billion galaxies, then we can see this rate of events. Okay, and this is the forecast. So this is the rate of events in O1, O2, when basically only the two LIGOs were on, then Virgo joined the game at the end of O2, so immediately the rate went up, because if you work a fixed alarm rate, one thing is to have a double coincidence, one thing is to have a triple coincidence, so a triple coincidence. And so this is the slope, basically, of the events of the order of 1.5 per week, since the 3 detectors are on. So all of the events up to O3 are published. The event of O4, you can find them online, but they are not published in the sense that they need some offline checking. And this is the plan. So you see, we are in this gray band between O4A and O4B. In O4B, Virgo will be joining with a minimum full sensitivity. It was sort of on here, but a very crappy sensitivity. So here we'll get back to the sensitivity it had in O3. Kagra will not really join in with a meaningful sensitivity until the end of O4. Then will be 2-year gap, and then will be O5. O5 is the last planned observation run for this generation of detectors. So it was said about the expected rate of length event with the advanced LIGO, Virgo, and eventually Kagra. So you should expect more than one length event every few thousand detections. So with the advanced LIGO, you shouldn't really expect length events. But then there will be the 3rd generation detector, and there will be the space detector, very quickly. 3rd generation detector will basically stretch the technology of advanced detectors, so laser interferometer on Earth, by going underground. By going underground, seismic vibration, they are mostly superficial. So you kill, not completely, but you kill some of the seismic noise. So the noise wall that you had at 15, 20 Hz can bring it down to 8 Hz, 10 Hz, 6 Hz. And so you can see more massive object, basically, up to very far away. And you have a better sensitivity. So basically, you can go and see object of few hundred solar masses up to redshift 10. Whereas LISA, you have an interferometer in space. So in space, there are no vibration. So basically, the size of the arm of the interferometer would be 1 million kilometers. And so you're really focusing, you start focusing supermassive black holes. So the peak sensitivity of LISA, the interferometer in space, will be around 10 to the 6 solar masses. Okay, so let me skip. So the one thing which is worth noticing is that, so this is advanced LIGO, this is 3rd generation detector. So they are called the Einstein Telescope or Cosmic Explorer, the analogous project in the States. So they 10-fold increase in sensitivity, but above all, you stretch the noise wall, you move the noise wall to few Hz instead of to 20 Hz. So this is the projected curve sensitivity for 3rd generation detector that should be active in 10 years from now. And this is the space detector. So a signal, this is a typical signal that we observe in advanced LIGO. You see it ends at a frequency that is fixed by the total mass, because the total mass is the total size of the system. So the inverse of the total size is basically the merger frequency. And then when you go back in time, the system was farther away. I'm wrapping up. The system was farther away, and then you basically you accumulate a lot of cycles for each frequency being, and so the frequency, the amplitude at the lower frequency is much higher. But the fact is that the time it takes from evolve from here to here, it can take years, or actually even hundreds of years. Whereas here, the signal we see in advanced LIGO, it lasts less than a second. Basically, the time duration to go from a frequency A to a frequency B grows as the inverse of the cube of the frequency. So if you move down by a factor of 2 the frequency you're looking at, you move up in the duration by a factor of 8. So basically, every factor of 2.5, 2.2 in frequency, then you have to be ready to expect a factor of 10 times longer in the duration. That's why most of the signal in LISA would basically, you see something here, and then after 5 years, it's still basically there. And there will be few golden events that you see here, and then after 1 year, you see there. So basically, the events of LIGO 1 2 years earlier in LISA will have a lot of other events that will move here in the years that LISA will be on. Okay, let me then skip to the end. So the idea is that how do we do the inference about the masses of the signal? Basically, this is a real output that you can download from the LIGO website. Here in this output of the detector, there is hidden the noise. You have to take a correlator with the with the pre-computed waveform, and then after you take this correlator and you divide by the noise. Basically, this waveform is in time domain. This output is in time domain. This is in frequency domain. You have to know the certain frequency being contain a lot of noise. For instance, what the frequency correspond to the oscillation frequency of the mirror. So you have to take this, make a Fourier transform, and then take out the content of this very noisy frequency, then go back to direct space. And then if the waveform that you have pre-computed matches exactly what is hidden inside the noise, no matter if you see this noise is very narrow, even though its amplitude is very high and is contributing to most of the noise in time domain, it's very easy to get it out of the correlation. So the idea is that you take this correlation and you are able to see very tiny feature of the fundamental signal. This is a double-edged sword because yes, you can take out spurious feature, but you need a very, very precise modeling. That's why for the future, let me skip. For the future, when we want to see, you see, this is what we are seeing. So this is expected rate of merger in the universe as a function of redshift. This is what we are seeing with the second generation detector. This is what we will be seeing for third generation detector. Basically, with third generation detector, at 2 redshift 1, we see all of them. When we are 2 redshift 2, we see 50% of them. So the idea is that, yes, how well do we need to know the waveform? So far, we have seen events that have signal-to-noise ratio of 20, 30 at the most. With third generation detector, we'll see the events with signal-to-noise ratio 400, 500. Again, to make a long story short, basically the precision of the waveform that we have so far is of the order 10 to the minus 3. Since the precision scales at the signal-to-noise ratio square, we need the 2 order of magnitude increase in the modeling of the waveform from now to 10 years from now when we'll have louder signal. And this 2 order of magnitude increase in the precision of the waveform will require a lot of work both on the numerical relativity that are now almost there, but not quite, but on phenomenological waveform, which is based on analytic computation. So analytic computation need to be pushed to a higher level than we ever done before if you want to match the requirement for third generation detector, which for few events, not for the bulk of events, we'll see millions of events, hundreds of thousands events per year. 90% of them will have the same signal-to-noise ratio as advanced LIGO now. 1% of them will have this large signal-to-noise ratio that we require in the modeling that we are doing so far. So the modeling we are doing so far will not be good. It will be good for the bulk of events in the future, but will not be good for the few golden events that we have intended for now. So for those, we really need to increase the precision, and that's why it's important to work on the analytic modeling of the waveform. Sorry, I'm 5 minutes over time. Thank you. So, yeah, so the memory effect is due to the fact that gravitational wave can be sourced by the by the encounter of 2 gravitational waves. So very close to the source, you have the energy produced by gravitational wave, and the energy, of course, is quadratic in the amplitude of the gravitational wave itself produced for gravitational. So it's it has a distinctive feature that since the energy is made by the product of two gravitational waves, each gravitational wave has a frequency omega. The product of two omega has frequency 0 or 2 omega. So the memory has the distinctive feature that it is a wave of 0 frequency. Okay, so this is very distinctive of the memory. So why? So it makes it very interesting because it's peculiar of general relativity and very hard to detect because it goes at low frequency. So with advanced LIGO, get it. With the third generation detector, maybe. With LISA, yes. So with LISA, it will be possible for and to see the effect and to eventually confirm or disprove general relativity. For third generation, it's marginal. Of course, the answer depends on some parameters, but to give an answer in 30 seconds, this is the answer. Yes, that is something that we have to take into account. So for the moment, the projection is the calibration can be kept under control to the 10 to the minus 5 level. This is the detector calibration error. Of course, the detector calibration, basically, the astrophysical parameter are they affect the phasing of the waveform, whereas detector calibration mostly affect the overall amplitude of the waveform. Of course, if the detector calibration is frequency dependent will also affect the effect. But the frequency dependence can be kept under control to this level. Not now, but this is the projection for 10 years. And so basically the idea is that we are really scraping the surface. The detector calibration can marginally be at the level so that even for the gold events is under control. Because again, it will screw the overall calibration, so the distance will not be as good as the distance will never measure to 10 to the minus 5. The distance will measure to a few percent at most. The distance that scales the overall amplitude. But you know, the phasing of the waveform, when you accumulate hundreds of cycles, then it's projected that can be kept under control to this level, which is exactly the level we need for the few golden events of signal to noise ratio of few hundred. If in maybe 40 years we have detect signal to noise ratio 1000 or more, then we're really, then there won't be any need to improve the waveform precision because those calculations will be there. But here, yes, we are marginally there. It's really there.
Aqui vai ser um desafio. Quer me ajudar? Se puder. Espero que não caia. Obrigada. Como é que eu... Aqui? Não, para trocar sim, mas a luzinha. Não é aqui? Morreu? Ah, aqui, ok. Aham. Okay, so I'd like to thank the organizers of this symposium. It's been very nice. And also the last two speakers, because they made my life much easier, because they've already talked about many of the things I'm going to talk. So a little bit of history. This is Jocelyn Bell when she detected the first neutron star. So it was detected in radio frequency, and it was something so unexpected that this booklet is a reality. So the case of the Little Green Man booklet really existed because people thought that there might be people somewhere else trying to talk to us here by very precise pulses. We know that those guys are pulsars, and those are the main manifestations of neutron stars. The pulsars themselves, that are powered by rotational energy, most of them are pulsars, and then accreting X-ray binaries, powered by gravitational energy. And then there are other guys like magnetars and so on, not as many as these guys here. And then I'm not going to talk exactly about them, but all of them are very compact objects with something like 2 solar masses within a radius of about 10 kilometers. So really very dense and compact objects. And somebody, he has already told us about NICER, that's the Neutron Star Interior Composition Explorer that was launched in 2017 and has already sent some data that I'm going to show soon. So in 74, these 2 guys, actually they were awarded the Nobel Prize in 93, but in 74, they claimed that this binary pulsar lost energy in the form of gravitational waves. So this was considered the first not direct detection of a gravitational wave until 2015, when this GW 150914, so it was detected on the 14th of September of 2015. It was finally detected by the LIGO-Virgo collaboration. And this was the result of 2 colliding black holes. And I'm not interested in black holes. I'm actually interested in neutron stars. So the first merging of 2 neutron stars that gave rise to a gravitational wave was in 2017. This guy here, GW 170817, and this was a very, very important event. Actually, it was afterwards called the multi-messenger event that gave rise to what we call now multi-messenger astronomy, because it was detected everywhere. So it was detected as a gravitational wave. It was detected in gamma ray, X-ray, ultraviolet, optical, infrared, radio. And so this is the first cover of the science in the cover of the science in this year that says that 2017 was a breakthrough. The breakthrough of the year was the detection of this gravitational wave. Okay, so this gravitational wave came from a galaxy far, far away. And it was observed electromagnetic by 70 observatories, as I said before, in all continents and in space, plus the LIGO-Virgo collaboration. And well, this last talk was very didactic, so I do not have to go through this. But what we do need is to look at these shapes that is based on general relativity simulations. And this is the in spiral, this before the merger. And this is what we get when the merger takes place. And this is the ring down. And this is the ring down. And this is the post-merger that has not been observed yet, as far as I know. Okay, so what does it have to do with nuclear physics and the constitution of neutron stars? So one of the important things is to calculate tides. And the first guy to model tides was this Augustus Love, and he just used Newtonian gravitation, and it was done in 1909. And his second name is Love. That's why many of the people talk about Love numbers. And those Love numbers, they characterized the formability of the compact object due to the external tides. 100 years afterwards, in 2009, these 4 guys extended the calculation to include general relativity effects. And I'm mostly interested on the second order Love number that's due to a quadrupole deformation. And well, this is wrong, but I think it was written in Portuguese first. This is 0.3. So the Love number of the Earth's tides is 0.3, and the Love number of neutron stars in this gravitational wave is of the order of 0.1. Okay, so again, the same figure. So the tidal figure of the companion induces this quadrupole moment, which accelerates this coalescence. And the time of the coalescence is determined by the tidal polarizability, which is this lambda, which is related to the second order Love number, which is this K2. We see that is the compactness of the object, so a relation of radius and mass, also radius, mass, and the gravitational constant. So how do we calculate these things? We need an equation of state. So the recipe is the following. From microphysics, both quantum and nuclear physics, we need an equation of state, and then we go to macroscopic properties. Or on the way from the equation of state to this macroscopic properties, we have to use these hydrostatic equilibrium equations, normally called TOV or TOV equations from Thoma, Oppenheimer, the Oppenheimer of the film, and Foukov. And so we use an equation of state as input, we calculate, and then we have as output some of the astrophysical observations. And then we confront our results with this, what the astrophysics, people from astrophysics tells them, and we see if it's good, good. If it's not good, we go back to the equation of state, we tune the equation of state, and then we try to improve the whole calculation. So, confrontation of equation of states with astrophysical results. Two of the important things are the mass and the radius. So after we compute things, our recipes comes out with this kind of curves, these shapes. Every point is one compact object. So the one here is the one with the highest mass, the most massive object, and this is its radius. 1.4 is a very important information, that those neutron stars with 1.4 solar masses, because they are the majority. So they are normally called canonical stars. So far, at least, they are the majority. And then this, if we come here at 1.4, we go and we see that these guys with 1.4 solar masses have this radius. So in general, the radii of the massive stars is lower than the radii of these canonical stars. And I'm going to show you soon why this is an important information. So we look at, in these works, for instance, we have analyzed the 35 equation of states considered to be good according to the nuclear physics point of view. And then we saw that just some of them reached 2 solar masses. But it was before this object was detected and then confirmed by NICER, which has 2.07 something solar masses. And then we can also look at this equation of states and obtain this tidal polarizability. 2 tidal polarizabilities because there are 2 compact objects in this binary system that are going to merge. And a good result is when we have these lines in between this 50% confidence line and 90% confidence line. So if we look at the equation of states that satisfy this constraint of 2 solar masses and the constraints of this LIGO and Virgo, 35 models, only 5 models survive. And these 35 models were taken from a sample with 263 models that I analyzed according to nuclear physics constraints. So you can imagine that I have many enemies around the world because I told them you work this equation of states that are no good to describe astrophysical properties. But of course, you can always improve things. And I'll show you some results at the end that really those equation of states can be improved. In April 29, NICER sent some of the first results. And when it was sizing up, so it was really telling us what was the radius of some of the most massive neutron stars ever detected. And it's nice also to look at the information of the radii, which are the constraints. So from GW 170817, we have this tidal polarizability, which is in between 10 and 580. It has no dimension. And if we look at this information, it reflects in the radius of a canonical stars in between 10.5 and 13.4 kilometers. Quite small. But then if we look at NICER pulsars, this is one of the canonical pulsars. So you see this is around 1.4. We have two results because two groups analyzed the signals of the detections, and they came out with very similar values with different ways of inferring the results. And this is this massive star I told you about. But if you look at these numbers, I've summarized here more or less. If you look, they have more or less, they very different masses, but then very close radii. So I will go back to my graph, and you see that to have a massive star with a canonical star with the same radius, the shape of my curve would have to be something like this and a very quickly drop, or something that the people call turn to the left, which is something that goes like this and then come back and then go to the tails. Okay, so this is not very easy to obtain from nuclear physics equation of states. Not impossible, but it's not terribly easy. So looking at those constraints, let's go ahead. We have those constraints, and then there was this paper where the authors claimed that these very massive neutron stars should have a quark core. So they analyzed the sound velocity in different matter, so quark matter and hadronic matter, and then they concluded that this massive two solar masses stars should have a quark core. So this is something that we expect if we look at the QCD phase diagram. So if we look at the QCD phase diagram, this is a different way of plotting it. I like it. It was proposed by Anna Watts. I like it because it's in log scale and the temperature, and then nuclear physics becomes very important. Otherwise, it's just a very tiny dot. But if we look at this region where neutron stars are, you see that they really can be hadronic matter. This is hadronic matter. Or they can be only quark matter, or they can be hybrid with hadronic matter with a quark core. So this is also a plot that shows this stellar evolution. And you see, somebody said, oh, white dwarf, neutron star, and black hole. So this neutron star can really be just composed of nuclei and leptons, of course, or quarks, or maybe something in between. And this was proposed many years ago. In 1969, these guys, Ivanenko and Kuchlazad, they proposed that hybrid stars could really exist based on this QCD phase diagram. And then 1997, Ito made the first proposition of quark stars. Then afterwards, this was studied by Bodmer and Wheaton, and so on and so forth. But here I have drawn these hybrid stars. There are two possibilities. We can have a hybrid star that's just quarks and hadrons outside, or we can have a hybrid star that has this mixed phase. So hadrons outside, a mixed phase, and quarks. And we can build this from a equation of states. I'm going to ignore these ones because the macroscopic results are very similar, whichever prescription we choose. And I'm going to show you just the simpler one. That's called Maxwell construction. So if I go back to this paper, the authors claim that this two solar mass star with a radius of 12 kilometers that coincides with nicer results should have almost one solar mass, which is about 40%, constituted of quarks. And this would correspond to a 50% of the radius of quarks. The question is, can we use equation of states and obtain this? Yes, we can. And I'm not going to enter into details. All models that I use are relativistic models based on mean field approximations. So I'm just I'm just going to tell you what's the prescription. So we have an equation of states for this quantum hydrodynamic model. So this is hadronic matter, and this is the black line. And then I choose 4 different models. This is based on the MIT Baggy model, which is a very simple model, but the MIT Baggy model itself is not good. And then I have also a vector interaction, and I have some sophistication of this MIT Baggy model. And then I draw these lines. This is pressure as a function of the chemical potential. And then I see where they cross. And then I see that if I choose this couple of equation of states, I have a tiny space of hadronic matter, and then I have quark matter. If I choose this one, I have lots of hadronic matter with a smaller quark core. So if we have appropriate models, we can build hybrid stars with different amounts of quark cores inside. And then we also have to see if I can get massive stars. And then I go to my recipe again, equation of states, the TOV equations, and the results. And then you see that this is the equation of states. Now it's the pressure as a function of the energy density. And then we have these gaps. I have this one, and in this one you can see smaller gaps because the crossing took place earlier. And then I see that with some of the equation of states, those are the results of the hybrid stars. I cannot get these two solar masses, but with appropriate choices, when I have these vector interactions, I can get these 2 point something. Okay. Oh, very good. And then this is very, this was from last month. And then people claim that this bizarre state of matter exists inside large neutron stars. And then more or less the same guys as the paper I've shown you before. They have now more sophisticated calculations to corroborate the idea that these massive neutron stars indeed are constituted of a quarky core. Okay, and then I'll go to some of the guys that Riccardo showed us before. One is this was obtained from this gravitational wave, 1908-94. One of the objects in the binary system was certainly a black hole because the mass was 25.6, but the other one was something like 2.6. So either it's the most massive neutron star ever detected or the least massive black hole. So there is this mass gap in between 2.5 and 5 solar masses, and that where the compact objects could be either one or the other. In this case, the signal to noise ratio was not good enough to obtain exactly the tidal deformability, so we don't know. And the question is, can we use appropriate models and obtain hybrid stars as massive as 2.6? And then before I show you the results, I'd like to show you this one. This is from last year. And then there's this guy here, it's called the Black Widow. And the mass is 2.35 solar masses, so even more massive than the other one. And the answer is yes, we can. With appropriate models, we can have hybrid stars. You see, you just look at the most massive stars. And moreover, we can have this strange shape when we have this 1.4. It's not, don't show it here, but 1.4 has this radii, which is very similar to the radio of this massive neutron star. The future has already been, Riccardo has already told us about it, so I don't have to enter into much details, but the idea is that NICER will be sending more information. Athena is going to be launched in 2030, and then there are these guys, ELISA, this evolved laser interferometer, and this Einstein telescope that's probably going to be ready by 2030, hopefully. And also, oops, the last one, which is this Cosmic Explorer, that's including LISA and the Einstein telescope. They working together are expected to send us lots of information by 2035. So it seems that the future is very good. We are going to have lots of information, and we are probably going to have more ideas about these compact objects. They are very, very different, very extreme. Okay, so thank you very much for your attention. The mass? Yes.
Is it possible that the chemical composition of the organic star affects the mass of the outcome clouds?
They all affect. So there is somewhere in here. Here, skipped this, not mentioning the hyper puzzle. So indeed, depending on the internal composition, we can have different masses. When we have extra degrees of freedom, normally the masses decrease. So if you have, for instance, some simple picture, just protons and just nucleons, protons and neutrons, and then leptons to ensure charge neutrality and chemical equilibrium, then we have a certain maximum mass. If we have the same equation of state with the same models and we include hyperons, lambdas, sigmas, and all, then the equation of state becomes softer, and as a consequence, the maximum mass decreases, and it may decrease a lot. What I just skipped this thing here because it depends on the coupling of the hyperons with the interacting mesons, and nobody knows exactly what it is, what those couplings are, the values of those couplings. So it's another degree of uncertainty that I just wanted to avoid in this stuff. Okay, I misunderstood your question. I guess so. Yeah, but I don't know. But I guess so.
Regardless of whether or not at quark center, you would expect one single line in this plot that you're showing, right? I mean, it depends on physical parameters, but the equation state has enough intrinsic room to change variables that you can actually move in between those lines for real stars in the universe, or the actual observation would all fall in a single line in there. And we're looking for parameters which can vary in terms of the physical conditions of the star for some reason, how fast it's spinning, or how charged it is, or what's the magnetic field, or we're talking about there has to be a single line relating mass and radius for neutron stars, period.
No. There can be many lines with different compositions that satisfy the constraint we have at the moment. There are not many. We do not have many constraints. We have the maximum.
Moment are limited by date.
Right? Yes.
But in reality, nature, neutron stars, they have so few degrees that I think it has to be a single line.
Oh, maybe if you go after just one single. Well, I don't think most people are looking at one single line because we rely on the information we have at the moment. At the moment, we have just a few constraints. And there are many, I wouldn't say many, but there are a reasonable amount of equation of states that can satisfy the constraints we have at the moment.
One equation of state, you have one line.
Oh, yeah, no. Well, no.
Yes, if I have one equation of states, I have one line, but I can have many different equation of states. Yeah.
And are you allowed to have this equation of states for different, let's say I have a real neutron star here, another real neutron star here, and the equation of states for these of the exact same mass. But I'm allowed to have two different equation of states for these two different stars.
Yes. So what you are asking me is if I can have, okay, and I don't know, another equation of state, 1 and 2. Yeah, I know. Yeah, wait, and then I have to come and look at whatever I know. So M and R, and then lambdas, and so on and so forth. And what we know is that we can have one equation of state that does something like this and satisfies my constraints. Okay, and then I can have another equation of state that okay, gives me something like perhaps this, and also satisfy the constraints I have at the moment. Okay, if other constraints come, then we have to retune and review my answer. But at the moment, I would say yes, we can.
Whether nature is just one.
Yeah.
I don't know. How can I know? Oh,
Well,
I don't know.
It's one theory, and the matter is a thing that whatever.
As far as it satisfies nuclear physics,
Yeah.
because as far as it satisfies nuclear physics bulk properties, okay, and the constraints these astrophysicists gave to me, I'm happy. Okay, if nature doesn't like that, we are going to know soon, whenever we have more information from both the gravitational waves and the telescopes and everything. Maybe this picture changes, and then maybe there is just one possibility. Some people just do it backwards. Some people just look at the constraints and find the equation of states. So, and then you can have more than one. Okay.
How many like PNS observed
Just from?
the
The observation of gravitational waves is not enough. It's not enough at the moment, okay? Because it just gives us this tidal polarizabilities and these love numbers. So it also tells something that it's completely, that's the crust of the neutron star and how to connect the crust to the core. So there's also more sophistication that has to do with nuclear physics that I didn't comment. So this is the gravitational, the tidal polarizability helps, but it's not enough because it does not say much except from canonical stars. Maybe perhaps, where is it? Here, you see? If we know this, then we can have a certain limit for the radii, but does not say anything about the mass. So we do have information, we do need information from the telescopes as well. Okay. Good. Thank you.
You know how is this? This is something like this. And it's turn on. Okay. Sorry, but it's not moving. The direction? No, but this doesn't work. It's not easier if I use my finger. No, this is the usual way, but it doesn't work. Yeah, but I want to go. Okay. I have this thing here. Probably I can just remove this.
So tell us about electromagnetics features of
A small second. Okay, thank you. Thank you very much. As it was mentioned, I'm going to talk about the electromagnetic signature that could be produced by supermassive black hole that are very close to the final merger. This is work done in collaboration with my former students, Eduardo Gutiérrez, now at Penn State, Luciano Combi, now at the Perimeter Institute, and with Professor Manuela Campanelli from the Rochester Institute of Technology. Sorry, something appeared. How do you push it here? Just press. I will try. Okay. You already have seen something like this. These are the masses of the black holes observed with LIGO and Virgo collaboration. This mostly are black hole mergers, and these black holes are of stellar origin. So when two black holes of stellar origin merge, essentially you should not expect an electromagnetic signature because this occurs in the interstellar medium that is not rich in gas. The electromagnetic signature only appears when you have a neutron star, but we are not going to talk about that here. Most of those detections in this frequency range around 100 hertz. If you want to observe more massive black hole binaries, then you have to go to lower frequencies. For instance, and around between 10 to the minus 2 and 10 to the minus 4 hertz, you can expect with LISA to observe some mergers from black holes of around 1 million solar masses. And if you go to lower frequencies at the level of 10 to the minus 8, then you in principle could observe the merge of really supermassive black holes with 1 billion solar masses. And this type of detections require pulsar timing arrays. So there are several experiments going on and accumulating data in order to make detections of this kind. Actually, last year, Nanograph collaboration communicated on the basis of 15 years of observations of millisecond pulsars, the detection of a gravitational wave background that is consistent in principle with signals coming from a population of supermassive black hole binaries. So what I want to discuss in this talk is what kind of electromagnetic counterparts we should expect from the moments of the month or years before the merger of these supermassive black holes. And this event should be rather frequent. We know that because galaxy mergers are frequent. These are real images of colliding galaxies, and these are simulations of colliding galaxies. Each one of these galaxies has a black hole, supermassive hole center. So if the impact parameter of the collision is not very large, these supermassive black holes can become gravitationally bound and form a system of binary supermassive black holes. And at the beginning, the orbit shrinks because of dynamical friction. And then the main factor that shrinks the orbit is three-body encounters with massive stars. And of course, in the final phase is gravitational losses. When the separation between the two black holes is of the order of 1 parsec or a bit less, then some phenomenology can be observed. One possible scenario, for instance, is when you have a very massive black hole and a secondary black hole with a smaller mass, that is orbiting the primary, and the primary has an accretion disk, so the secondary goes through the accretion disk. It will go through twice per orbit, producing strong, large thermal flares. And these perturbations of the disk will produce waves, density waves in the disk that will feed the black hole. And since there is a coupling between the black hole and the accretion disk and the jet, you can also expect some non-thermal flare from the relativistic jet. This is the situation that it is thought to occur in this very famous object, OJ 287. The light curve shows periodicity, quasi-periodical signals, and there is a very detailed model developed by Baltonen and co-workers, and they have predicted the flare that occurred in 2015 and the subsequent non-thermal flare from the jet. So this is a nice example of one of these systems. No. This is another galaxy. Yes, this is an AGN. Yes, exactly. With the jet and all the thing. This is not our galaxy. Another possibility, when the two black holes are now in an orbit that is almost coplanar with the accretion disk. This is the primary black hole. This is the secondary black hole. The innermost part of the accretion disk should be inclined, mostly in most cases because of different type of instabilities, with the orbital plane of the two black holes. And so the secondary black hole can make a torque on the inner part of the disk, so the inner part will precess. And because of the disk-jet coupling, the jet also will precess. So if we can observe superluminal components ejected by the jet, we will observe some pattern according to this precession. And for instance, in the case of 3C273, that is another very famous AGN, we have been observed this quasar for a long time, since the 60s, because this was the very first quasar ever detected. So we know many superluminal components that have been ejected. We know the velocity of this component and the time when they were ejected and the angle in the sky that they were ejected. So you can fit very well the pattern of these superluminal components in the sky, assuming that jet is processing with this mechanism. So this could be another electromagnetic signature. Now, when the black holes are closer, we have a self-lensing if the viewing angle is the right one. So here you can see some simulations made by my student Eduardo Gutierrez. Here you have two black holes in a very close orbit. Here you are seeing the system edge on, and each black hole is surrounded by a small accretion disk, what is called a mini disk, and also a corona of a hot gas. So when both black holes are aligned with the line of the side, there is a magnification of the light from the black hole that is is behind the first one, and this results in a variability pattern, periodicity that can be observed. If this is an animation, so it follows what is going on here. So you can see that there is a maximum each time that one black hole makes the occultation of the other one. And if you have jets in this type of systems, also you can expect some magnification of the base of the jet by the black hole. And this is non-thermal radiation. So you should expect thermal and non-thermal flares in this type of events. And then when the black holes are really close, the situation changes with respect to what happens in the case of a single black hole. In a black hole, you have the black hole and then the accretion disk all the way up to the last stable orbit. And you could have a corona around the black hole and above the accretion disk, and that's it. But if you have two black holes, here I am considering two black holes of similar mass, then if they are very proximate, they remove the gas in the inner part of the accretion disk, so they create a cavity. The size of this cavity is more or less of twice the separation between the two black holes. And so there are several components here. We have first the circumbinary disk that is more or less like the normal accretion disk of a supermassive black hole. And then we have the black holes, and each black hole is fed by a stream of matter that comes from the circumbinary disk. And since there is a lot of angular momentum being transferred, many accretion disks are formed around each one of these black holes. This can be corroborated in simulations. For instance, these are simulations made by my student Luciano Combi, where you can see all these components. So one black hole, the other black hole, this is the cavity, this is the circumbinary disk, and there is a hot feature that you are seeing here that is called the lamp. I will show that in another slide. So these are simulations made with black holes of the same mass. So both masses are the same. So the basic components also can be seen in this simulation. This is the lamp in the circumbinary disk. We have the cavity and also the streams that provides matter to the mini disk. And this is the evolution of the entire system. So there is a growth phase when you start the simulation, and as time goes by, there is a relaxation behavior of the accretion rate onto the system, and finally this accretion rate is modulated by the bit frequency between the lamp and the mini disk. So we have a quasi-periodic behavior of the accretion that, of course, is translated in a quasi-periodic behavior of the light curve, in this case, the thermal. So if we want to know how the spectra of these things evolves, the spectral energy distribution, we need to calculate the contributions of each one of these different parts. So this is the simulation, and this is the behavior of the radiation that is being produced by the different components. The components are separated here. This in blue is the circumbinary disk, this part here. And you see that it dominates at optical frequencies and up to ultraviolet because it's colder. This part of the disk is colder. And then you have the contributions from the stream. The stream contributes strongly in the ultraviolet, but the contribution from the outer part is stronger. So mostly is not important for the overall shape of the spectral energy distribution. And then you have the contribution from the mini disk, 1 and 2 mini disk, and you see that the mini disks completely dominate at high energies. And this is because the mini disks are hotter. And essentially they can comptonize radiation from this part and produce higher energy radiation up to hard X-rays. And what about jets in these systems? In principle, if a magnetic field is also transferred from the circumbinary disk through the mini disk, each one of the black holes can produce jets as normal AGNs. What is the evolution of these jets? Well, these jets are essentially point flux dominated jets. What happens is that the magnetic field, essentially poloidal magnetic field, is accreted by the black hole. When the magnetic field enters into the ergosphere of the black hole, then a toroidal component develops. This produces magnetic pressure in this direction, and then there is a Poynting flux escaping from the system that can be roughly calculated if you multiply the magnetic energy density inside the ergosphere by the cross section of the ergosphere times the speed of light. So this is essentially something that is proportional to the square of the magnetic field and to the square of the mass of the black hole. So you see that if you have a maximally rotating black hole and a typical magnetic field of 10 to the 4 Gauss, and for a supermassive black hole of 10 to the 9 solar masses, you will get an extremely powerful jet of 10 to the 46 erg per second. Okay. So this is the mechanism, but now we have two of these jets, and these jets essentially are confined by the external medium, so they should expand. So you see both jets expand as the jet goes away from the black hole. The toroidal component of the magnetic field becomes dominant, and at some point both jets will interact. This is corroborated also by simulations. This distance is should be around 100 gravitational radii, something like that. So everything is magnetically dominated at these distances, very close distances from the black holes. So we have the interaction there, and what happens then is that we have true magnetic fields of different orientations. So recombination is expected to occur in a region that also should be turbulent. And under those conditions, particles can be efficiently accelerated by turbulent magnetic reconnection, for instance, as shown by, for Del Valle, Vete d'Alpino, and Cowell. So then we have the production of non-thermal emission in the system, and this changes the shape of the spectral energy distribution. These are just two examples, one with low acceleration efficiency and one with high acceleration efficiency in the reconnection region. So here you see the contribution from the circumbinary disk and the mini disk. Both mini disks are added in this plot. And then you have synchrotron radiation. This is synchrotron radiation that is produced in the reconnection zone, and inverse Compton radiation. And everything is suppressed here because of photon-photon annihilation. And also at more or less infrared energies, also we have suppression of the synchrotron radiation by self-Compton absorption.
Say exactly where what would expect to see in specific pictures of this, which are not going to be in regular AGNs, because this
Yes.
It's expected on the AGNs, right?
Yeah, it's similar, but in this case we have these two humps here, and then you have a strong emission at let's say high X-rays, but it depends on the efficiency of the acceleration. For instance, synchrotron radiation here can extend up to almost 100 MeV, something that is very difficult to obtain if you accelerate particles by shocks, because you are very close to the limit of the efficiency for shock acceleration. But that is not a problem if the acceleration is by magnetic recognition. But perhaps the best answer to your question is in this plot. If we increase the magnetization, let's say magnetization above 10, then this very peculiar feature at around 10 MeV appears. This is a very difficult range for observations, a few MeV, but this is very peculiar and has not been observed in AGNs where we know that for sure there is just one single black hole. So this is the main prediction. And this is the behavior of all, yes, I know, of the spectral energy distributions for this type of system with two jets interacting in the magnetic reconnection area with what I'm showing here is how the set changes with the separation between the black holes, with the Lorentz factor of the outflow, with the mass of the black hole, and with the viewing angle. And well, I do not have time, but I think that you can interpret the figures by yourself. Just one final comment is about what are the time scales of these events. In the case of the flares, well, it will depend on the mass of the black hole and the separation between the black holes. If we assume a system of redshift of 0.2, so you get these values. For instance, for a separation of around 100 gravitational radius, you have time scales of the order of 10 to the 5, let's say, less than 1 day for a black hole of a bit more than 10 to the 8 solar masses. And the orbital, the periodic signal, because there will be a periodic signal, especially if the jets are inclined, they are not parallel because they will interact just twice per orbit. Well, you can infer it from this other picture. I have my conclusion, but no time. Sorry? Well, since you know the entire spectral energy distribution, this will occur at different frequencies. So essentially, it will occur in gamma rays at MeV energies, and also you can observe this at the radio wavelength. And in the optical is more difficult because you have the contamination from the thermal radiation that comes from the circumbinary disk. So radio and high X-rays, gamma rays are the best energy ranges for this. Thank you. Sorry, bigger. Well, all this is extremely new. This simulations is extremely new. So I am not aware of any attempt from observers to detect this kind of signatures. I know that there are some AGNs with some bump already known at MeV from the times of the Comtel instrument on board of the Compton satellite a long time ago. That was the last instrument that could observe in that energy range. But since there is no new MeV observatory in space, it's very difficult to detect these things. So right now, the best chance is, I think, in radio. Thank you.
Very much. My talk will be about the question if one can bring quantum gravity aspect into gravitational collapse. Of course, right from the beginning, you can ask yourself which quantum gravity. There are several candidates on the market, and depending roughly which aspect of general relativity you emphasize, the geometrical one, you might end up with triangulation, or the field theoretical one, you end up with the canonical quantization. And I will choose the later one, canonical quantization. And the second question is, why do I expect that there will be quantum effects in the collapse? Of course, not in the early stage of the collapse. There's a dust starts collapsing. This is not what I mean. I mean quantum effects in the late stage of the collapse. Okay. Yeah. Okay, so I will essentially I will talk about the gravity. The Robertson-Walker metric appears in two places in cosmology, but also in gravitational collapse. And around 1980s, there were hundreds of papers literally considering essentially quantum effects in cosmology using this method. This is why I believe essentially that I can use the same for gravitational collapse and get also some quantum effects. And as I told you, I am concentrating on the canonical quantization. So I will have Wheeler-DeWitt equation at the end. I will have Wheeler-DeWitt equation as a result of the canonical equation, and it will appear in both. It appears in both. There will be a Wheeler-DeWitt equation in cosmology and Wheeler-DeWitt equation in gravitational collapse, which look very similar. The Robertson-Walker metric used in general relativity. The difference is how to derive the Robertson-Walker in cosmology and gravitational collapse. There is a difference, okay? But they have, of course, this is the Robertson-Walker metric. They have common features. In both cases, you choose cosmic coordinates. You move with the cosmological flow, or you move with the collapsing method. This is the one thing. And in cosmology, one derives this metric on principles, homogeneity and isotropy, the cosmological, also called cosmological principle, isotropy, and Weiss's principle, which would correspond to homogeneity. Essentially, I believe this is the existence of the common coordinates. Okay. In cosmology, the R, the small r here, is dimensionless, and the capital R is dimension x. And the k is plus minus 1, 0, corresponding to the geometry of the spatial space. In gravitational collapse, it is not the same. In the cosmology, one doesn't use Einstein equation to obtain the answers for the metric. In gravitational collapse, one uses essentially resetting the block, which corresponds to the choice of the coordinate, and one uses Einstein equation to derive. One start with a general metric, one start with a general metric here, with a very general metric it has some 5 elements, then four elements, depending on ID, so it's symmetric. Resetting the clock, choice of coordinates, reduces to 2, they are called Gaussian normal, you use Einstein equation, you get the side, it goes over ranges, it goes over ranges. And K here is not 0, 1, 3, it is a value, it is a value. Okay? Otherwise, it's the same. Let me tell you right from the beginning, in all many quantum versions of gravity, we have one problem, the absence of gravity. You cannot do dynamics, you cannot chronologically, I mean you can, nobody knows something like this. This is because we are quantizing space by itself, right? We are not standing here. Say the coordinate R in Schwarzschild, the Schwarzschild is the R which we measure at the end. The T in radar echo delay is the T of the metric. So you cannot step outside the metric. It's why there will be no space, there will be no time, which essentially is not like you can take an atom, you can put your coordinate system, or you can put the time of the observer, and it's your part of the space time. You are part of the space time, and you cannot go outside. This is why you cannot sit down. T of an observer. It is done. In no journal it is done. This is clearly not the case here. Okay. This gave rise to many articles, many books, articles, many articles where the heck is time. Is the problem of quantum gravity. Nevertheless, we can gain insight very the absence of time is important. Very briefly. It is called, how would I proceed? I need to separate dynamical variables from not dynamical ones. This is because it is like in a gauge theory, it is a huge symmetry. There's a huge symmetry involved. So you essentially slice the space-time of variation. Just to have a topology, hyper 3-dimensional hypersurface cross R, which corresponds to the T. You have to have the equation for the T, and you proceed like this. You get essentially, then you have a projective delta here. So a tensor can be projective, especially this one here. And then, if I show you equation here, you cannot follow it. You cannot follow it in 20 minutes. I'm showing you just to show you for the thing how it is, and then you can write geometric in terms of a function n, which is collapsed, and I and hi. You can write it. Now, still nothing has come out. The collapse function, shift vectors, and free metric. It will turn out that the limit equation that these are not dynamical variables. The only variable that's why there's no time. Okay, this is 2015. Rich Arlovitz, Deza, and Mishna celebrated 50 years the anniversary of the ADM decomposition. It's long. And it will be for us for even longer. This is because in quantum gravity there's lack of experiment. So we can do anything we want, right? We can do anything we want. Okay. So how will I quantize now? I need the action, Einstein-Hilbert action. I have to write the Einstein-Hilbert action in the large function shift vector and free metric. Okay. There will be an external curvature because you have essentially this hypersurface and maybe for dimension. Okay. And then once you have it, you take the canonical momenta corresponding to the three functions. You take the canonical momenta, and something happens. This is not zero. But corresponding to the shift vector, the corresponding to that function is zero. It's not dynamic. These functions are not dynamical. This was the purpose of the so-called ADM decomposition, to separate dynamics from constraints. Separate dynamics in direct terminology of constraint system that implies rather singular, put it in whatever way. They are not dynamical, they will play a role of Lagrange multiplier if you would continue for Hamiltonian gravity. Then having, so it's ambitious to construct the Hamiltonian density with Hij, okay, and the Hamiltonian is done. It's the integral of the density with the hypersurface. They are second constraints, they are only constraints. They are called secondary Hamiltonian constraints, okay? The ADM also doesn't depend on my and n. Okay? And one of them is exactly the way that we it's a constraint. It's a constraint, okay? It's a constraint, and using the so-called bit metric, you can now rewrite it in the better form for I include also the scalar field development. And then you quantize. You quantize by taking the momenta as derivatives, right? As derivatives, and researchable equation, then you will not get any time. As expected, essentially. As expected, you don't get any time. Okay, and this was on the space, but time is how will you make dynamics, right? How will you make dynamics? Okay. Now, as I told you, around 1980, people have used the Wheeler equation for cosmology. Based now, the matrix elements will appear, based now on the Robertson-Walker method. And as I showed you also, arithmetic appears in gravitation columns. Many people take this. Many people still take that up today. Now we can simplify that. This is because Robertson-Walker is simple. Okay? Ansatz for metric into Einstein equation. The resulting equation can be derived from a Lagrangian, the inner ensemble, a mechanical system. The quantization can be done immediately. You don't need to go back to the Hij. It should be the same. Only you should remember not time. And this can be done. Remember, I have to rescale. If I go, the gravitation collapse, which I'm doing. So this has length. This is dimensional. I can rescale it. I have a typical length 1/√k, and then it looks like the Robertson-Walker method for cosmology with k equal 1. So it is right. And it should be. Okay. Then I need to rewrite the action again. And I can rewrite it. That is not going to be there. For the Robertson-Walker method, this is the result which I'm using. I can rewrite it, and here I have a Lagrange. I don't need to go to the complicated general Wheeler equation. I can even include matter, and matter will have this form here, because it will have this form here because of the conservation. Then I have a canonical momentum of the Lagrangian. I have a canonical momentum, and I have the Euler-Lagrange equation. And this Euler-Lagrange equation comes exactly as one of the Friedmann equation. Right? Exactly as the Friedmann equation. So now we have the Lagrangian, we have the canonical momentum, we have the Hamiltonian, then we quantize it. And we can number of bands. Okay. That depending on the equation of state. I go back to my coordinates, and I can divide it. In this way here. Simple potential. It's a simple potential. After all these efforts, right? What comes out is a simple potential. You can declare the cosmological constant in our universe you can neglect it. Because the vacuum over zero is much smaller than prime density over zero. Then you get this one here. You can shift it a little bit to see what comes out. You can define a new variable argument, and you get such an equation. Yeah. Now, if you look in quantum mechanics books, this equation is the equation of harmonic oscillator. With small differences, I have an A from 0 to infinity, harmonic oscillator from -infinity to infinity. And I have another, since I have redefined my variable, I have another argument. This and I have also exactly a harmonic oscillator same. The book Griffith's quantum mechanics. And now you insist on square integrability like in harmonic oscillator. It is not more or less a test thing. You get better. You get K quantized. You get K quantized. Remember K is beta. It's not beta has to do with Rogerio. Otherwise, everything is. Yeah. Okay. So you get the quantization of the central density. The quantization of the central density gets quantized in terms of the prime density. And the continuum that's not really, it's not the hydrogen atom, which was 1 over n squared, but the continuum switches to large n. For large n, this will be much less than prime density. The ground state is a ground state, and they are excited state, which are essentially the exponential into the minus psi square, and repeat polynomials in this variable, and this variable is quantized. This different harmonics. But has good similarity with harmonic oscillator. Also, the process of the ground state, the wave function square avoids the central singularity. A0 is not there. Right? A0 is not there. Higher excited state, you can see their preferred values. It looks like this is 0. No, but here you will some preferred value. Space time is quantized from this. It's not exact, but there will be preferred values with the matter will be. So it looks promising because it's exactly what I would expect from such a theory. So far so good. Now you should interpret it further. As long as you stay here, it's okay. But if you go to interpretation, a scientist goes to further interpretation, he runs always a danger, right? There's always a danger. So if you rewrite rho zero, right? All matter is beyond inside the Schweitzer. The A tilde, sorry, but was a small mistake. This should be A tilde. So the A tilde becomes 1. So it looks like A tilde I could eventually identify with the Schweitzer radius. Okay? And then if it's 1, you can see there is a small leak. Right? There's a probability to be outside A tilde 1. Be outside the horizon. So it's either the horizon is fuzzy, no good interpretation, or there is some kind of interpretation. But we have to relate it. Like right now I have done it, right? Then the interpretation is the black hole at the end, towards the end, I'm going with there is no Schwarzschild as such, because I'm going with the matter. I'm probing the matter. Right? I'm shooting different coordinates. No Schwarzschild coordinates. The black hole de-excites in some discrete way. Right? De-excite. That kind of like an atom, very roughly, in a discrete way. Via a discrete version of population, which for the classical limit can be, would be the population. And which is the ground state. Remember, there's a ground state wave function with N0, which then would correspond to the black little bit different, from home radiation. Do I have 2 minutes? And 1 minute? Of course, we are not alone in the universe, and there are other physicists, right? There are other physicists, and the other physicists on my talk is based on a paper which appeared this year, and one which is confirmation. But there are other papers which use Robertson Walker method to talk about quantum effect and Nathan Rosen, the famous guy. He's from the Einstein Podolsky Rosen, is the same guy. But then he wrote a paper. But his potential, for some reason, is not within the weak potential. And has a so it's been expanded, this has been expanded. There are also other papers, quantum gravitational curve, and so on and so on. However, they all use time. They all use time as a result. Not the density is quantized, energy, they will have separation then. By separation, they will get an energy. There could be others. The problem is the time always, right? The problem is the time always. The gravitational collapse can be also classical. So to check every paper on gravitational collapse. Thank you very much.
This random, assuming that the random they say that if we have a super light record of this random view of that method, like a form of that method. Maybe
it's a random black hole. Which does not have any more open gravitational fields. What people?
Não, não é que a gente quer.
Escolhe essa. Qual é? Se for decidir, qual é? Mas a gente consegue satisfazer por enquanto.
So my chair is not here, so I started off. Your chair was looking like my chair in front of you. So how was Ricardo was looking for.
You don't need a chair.
I don't
You're
need
the
a
boss. Go
I
ahead.
know the boss.
This way?
I can control your house.
Yes, please do, but I will finish soon enough. Okay, so Sturani. So sorry, I introduced myself. I'm Rogerio. It's very nice to be here. Thanks for the invitation. So I'm going to talk mostly about LSST in Brazil, and Martin already said a few words about LSST. So I will continue, and then I will concentrate on what we're doing in my group here in São Paulo. The chair is late. I'm here, as usual. Okay. So I already introduced myself. So this is my chair, by the way. Let me introduce you my chair. And my chair is going to be for my time. So this is Riccardo Sturani, my chair. Okay, so the idea that what we want to do is to test our very successful model of the universe. And the very successful model is Lambda CDM, which so far has passed all the tests that we have. There's some tensions, and Raul mentioned the Hubble tension. But so far, we believe that this model describes from the very beginning of the universe, especially from the CMB, where we have very precise data. We have also data from 3 minutes after the Big Bang, from Big Bang nucleosynthesis, and up to today. And
the idea is to test the consistency between the CMB experiments, so very precise data about the universe when it was about 400,000 years old until today, where we have galaxies to test cosmology. So this is a non-trivial test of the model, and that's what we want to do with the surveys that are being conducted in galaxies, and that's which is here. Okay. Now where's the here? Okay, so there are two types of galaxy surveys. One is the galaxy survey that takes the spectra of objects, and this has very good quality of redshift measurements, but usually has a small number of objects because you need to take data from each object and collect the light, etc. And then there's no imaging, there's no photograph. You should take only spectroscopic data. The other type of survey is what we call photometric surveys, and where we take pictures of galaxies and different color filters. So and sometimes if you don't have many filters, like Raul was saying, they have about 50 something filters, so it's much better quality, but usually you have 4 or 5 filters. And then you can have a fair quality photometric redshift estimation from it. On the other hand, you have a very large number of objects. You don't have to know where the objects are in the first place. Here you do have to know where the objects are because you have to place optical fibers on top of each object. Here you don't have to know, and you take pictures and have many more objects. And then you have also the pictures of the objects. You have photographs, and you can study the distortions of the shapes of the objects due to weak gravitational lensing, which Martin talked about. So I'm going to concentrate on the two photometric surveys, the dark energy survey and the legacy survey of space and time, and they're both photometric surveys. So and the spectroscopic survey, I think Martin also mentioned, or Raul mentioned, is the dark energy spectroscopic instrument that is given targets for JPass. That I think you mentioned that, or didn't you mention that? Or you give targets to DESI? Someone mentioned DESI. Wasn't that you? Okay, so maybe okay, so this is the a report on the topical group on dark energy and cosmic acceleration from SNOWMAS. So this is a study done in the basically from the US, and these are the different experiments that in the cosmological landscape. And yeah, there's several experiments. DESI, this is Rubin. I'm going to talk mostly about the Rubin Observatory. This is the dark energy camera. This is CMB experiments, gravitational wave experiments. This is an experiment on the dark side of the moon. And this is some 21 centimeter experiments. Okay. And also I want to mention that recently, last year, December last year, a report came out from the what's called the Particle Physics Project Prioritization Panel from the Energy Physics Advisory Panel for the Department of Energy. And the first recommendation as the highest priority, I just want to mention that there are 3 recommendations as highest priority in the third. So it's high luminosity LHC, and DUNE, first phase of DUNE, and the Rubin Observatory, especially they're giving support for the dark energy science collaboration of the LSST. I'm going to talk a little bit about this. So Martin already mentioned, I just go a little bit over what LSST is. It's a 10-year survey that's going to be conducted at the Vera Rubin Observatory in Chile and at CTIO, Cerro Tololo International Observatory, using a brand new telescope. It's called the Simony Survey Telescope. It's an 8.5 meter primary mirror with almost 10 square degrees field of view, and has the largest ever built digital camera, which is the LSST camera with 3.2 gigapixels and 6 filters. And the construction started in 2015, and there are 10 years of observations that they're planning starting next year. There were lots of media recently about this camera that is being shipped to Chile, and this I just put a few of these things in in Portuguese actually. So maior câmara digital, etc., etc. This is actually Aaron Rudman. He's in charge of the building of the camera. This is a picture I took when I was visiting SLAC. So this is being built at SLAC, Stanford Linear Accelerator Center in the US, and it's going to be shipped to Chile very soon. Okay, so the science of LSST is again, it's very broad. You can do much more than just study dark energy. It's going to be a huge amount of data, and this can be used for multiple science goals. And these science topics are addressed in this LSST science book, which you can actually download from the internet. And the science topics, they are addressed within LSST in different autonomous and self-managed LSST science collaborations. And the science collaborations are 8, and I think Martin already mentioned 3, if I'm not mistaken. There's a collaboration active galactic nuclei, one on dark energy, informatics and statistics, transients and variable stars, Milky Way local volume, strong lensing that Martin mentioned, galaxies and solar system. Okay, so I'm going to talk a little bit about the Brazilian participation in LSST. There is what's called the Brazilian Participation Group, or BPG. I'm the current coordinator of this group, and Thaisa Stork Bergman is the vice coordinator, and Tassia Ferreira is the spokesperson. And there was an MOA signed in 2015, which granted 10 principal investigators for LSST. And for each principal investigator, you can also have 4 juniors associated, so it could be postdocs or students. So, this is 50. And more recently, an additional 16 principal investigators, and then 16 times 4 is 64 juniors, so 80 people in total were secured by this laboratory through in-kind contribution. So we are already 2 years of full-time contributions that were given to LSST and was successfully reviewed by Rubin. There is a project in Brazil, it's called INCT, Instituto Nacional de Ciência e Tecnologia, that is giving full support to the Brazilian participation in this project. And then there's an in-kind contribution, which is basically building what is called Independent Data Access Center, plus data products for the determination of the photometric redshift of the objects. And then also some pipeline scientists are involved. And these are some people that are involved in this project. Okay. So at the moment, the Brazilian participation group at the LSST, we are 23 PIs and 76 young researchers, and Argentina and Mexico recently joined LSST. And I think Martin also mentioned Chile is a native member of LSST since the observatory is in Chile. So this is an article that we published in the Revista Brasileira de Astronomia about the Brazilian participation at LSST. If you want, you can read it it's online. Now, I think it's very nice that we are organizing a Latin American LSST meeting for the first time. And this is going to take place in La Serena, in Chile, in June 10 to 14. This is very important, and registrations will open soon for this. And this is an effort from all the participants. So it's going to be very important for people to register and participate. And also, Martin mentioned these Think brokers. There's going to be a meeting, a workshop of these Think brokers in Rio, I think. And this is in, what is it, May 5 through 10. So this is also, again, is independent of LSST, but are the people that are going to have access to millions of alerts each night from LSST, and they're going to look for transients. So these are 2 things that keep in mind that these workshops will happen very soon. Okay. So now I want to change gears a little bit and talk about what we have been doing here at ICTP-SAIFR. So I'm a member of the LSST Dark Energy Science Collaboration, which has more than 1,000 members, more than 20 countries. It's by far the largest scientific collaboration with LSST. And that looks for dark energy, dark matter, weak gravitational lensing, many things. So what we want to do, again, is to learn about dark energy and dark matter, and mainly from the combination of observables such as the distribution of galaxies, so how galaxies are distributed, and that gives information about the underlying cosmological model, including something called the baryon-acoustic oscillation feature. Also, information from the distribution of the shapes of galaxies. So this is weak gravitational lensing, supernova type 1a, and how many clusters of galaxies are there. And also, we want to do this in combination with external data from CMB, for instance, Planck, ACT, Simon's Observatory, S4, gravitational waves from LIGO, Virgo, Cagra, etc. Whatever external data we can use, we can combine and get more and more stronger bounds on the cosmology. So a little bit about the dark energy science collaboration. So we are divided in many different working groups. Now there's weak lensing, modeling and combined probes, which is the one I'm mostly involved with, where Tássia Ferreira, a Brazilian who is also spokesperson of the Brazilian participation group, she's the co-convener of this working group. So there are lots of different working groups, and many people are working on different aspects. I just want to emphasize that two people that are related to our groups, Felipe Andrade Oliveira was a postdoc here, and now he's a postdoc in Zurich. He's one of the responsible for the covariance matrix effort, which is important for statistical inference. And Sandro Vitente is a pipeline scientist of LSST, and he's working on a likelihood framework, again, for statistical inference. So this is the dark energy science collaboration. Again, this is one of these collaborations, okay? So I'm going to talk about some of our work. This is a work that's still in progress with a former master student, Abdiya Zaides. So we're trying to mitigate the nonlinear galaxy bias. So this is the relation between dark matter distribution and galaxy distribution. We call it galaxy bias. So we are still working on I think Raul was in the committee of now you remember, right? So we're still working on that. It's not finished, okay? And this is I work with a PhD student, Diogo Henrique Francis de Souza, and this is trying to resolve this Hubble tension using, so one of the models that are most used to solve, or at least ameliorate the Hubble tension is so-called early dark energy models. But then you have to explain a little bit more about these early dark energy models, and there's a neutrino-assisted early dark energy model. So this is some work that Diogo has done. And this is another PhD student here at the FT, João Vitor Rebouças. He also worked on early dark energy models, but then combined with modifications of late dark energy models. And so this is the work was just accepted for publication, where we have a model of early dark energy. So it's usually an axion-like model. I can go in more details if you are interested. But we also changed the late time expansion to see how that can affect especially another tension that Raul did not mention is called the SA tension. That it's not as high statistically significant, but still. And he's also, João is also working on emulators from some simulations for assessing nonlinear scales at LSST. And then there's a postdoc, Louis Legrand, who is working on incorporating V-lensing into TJ, the covariance matrix, so external data with the future LSST data. Also a member of Euclid and Simon's Observatory, so that he is just an example of a covariance matrix, not a final one, of course, that he obtained. And Walter Riquelme, he's a postdoc recently arrived at ICTP, and the project that we're developing is to search for primordial non-Gaussianities in two And he already led the effort of primordial, exactly this project for the dark energy survey. And this is the paper of the dark energy survey that was published also, well, was last year, and Walter was the main author of this. So we are submitting a project for the working group desk of primordial Gaussianity. And we want to check with some simulations that are already available. And finally, you have to be careful with the pictures that you put in the WhatsApp. Where is Ricardo, my chair? So Ricardo is also an external collaborator of LSST, and he's worked on cross-correlation of gravitational wave events with large-scale structure. So this is more or less the work that we are doing here at IFT. Not all this work is related to LSST, but some of them are. Okay, so I'm finishing. Conclusions are that the Rubin Observatory's LSST provides incredible number of data. There is a very rich science program with this LSST data ahead. Amazing opportunities, lots of challenges. There are 8 science collaborations. There are many, I forgot to say, but we have 100 scientists, I think I said that, 100 Brazilian scientists already working in LSST, different science collaboration. So I just talked about the dark energy science collaboration. There are many people working the active galactic nuclei collaboration, especially from the South Thais and group and more people in Milky Way. Many people work on globular clusters, etc. So there are people that are distributed among these different science collaboration groups. I just talk about the dark energy science collaboration because that's the one I'm involved with. Okay, so we're getting ready for the real data. There are data challenge, data preview catalog. So we're testing lines, various. That's the stage we are at now. So the Brazilian participation group, it's already engaged in several science collaborations. Many of us comes from the dark energy survey. So the dark energy survey was the previous photometric survey, finished taking data in 2019. And we're still analyzing the full 6 years of data that was taken. And this year will be the release of the final analysis of these 6 years. So it's actually Monday, tomorrow, there will be 3 papers on the archives about the BAO results, the final results of BAO results, which actually had a very important contribution from a group from ICTP. Hugo Camacho led the Fourier space analysis of the BAO in DS. Anyways, so this will be tomorrow on the archives. Argentina and Mexico recently joined, so there are opportunities for collaboration. I think this is very important. So the group in something else people are doing in Córdoba. It's Mariano Dominguez and Nelson Padilla. They're both in Córdoba doing excellent work. So we are talking to them about this that is going to happen. Actually, it was supposed to happen in Córdoba, but then Mariano said, no, after the election, we cannot do it. So we're doing it in La Serena. And it's the first time there's going to be a Latin American meeting of LSST. I think there are exciting times ahead, and we're really waiting for the first LSST in 2010, and I finish on time. Thank you. It's here. My chair doesn't pay attention. Waterfall. He was distracted by this. Yeah, so it's the beginning of 2025. So the camera is being shipped to Chile, and they're going to make, I think 2024, we're going to make the first tests, really.
all São Paulo session. Now you can tell us about baryogenesis.
Okay. Thanks for having me here and all the audience for being here on a rainy Sunday. So today I will talk, this is the topic of my talk. So I was told to give not a talk for general public, but I now change my title. So I'm from Federal University of ABC. And I will talk a bit about baryogenesis. So I'll give first an introduction about the history of our universe. So we have heard about the late universe. So we have when the cosmic microwave background is produced, when the temperature of your universe is about electron volts, and when your universe is a bit hotter, mega electron volts, we have the formations of light elements. The proton and neutrons they fuse to form deuterium, helium, etc., up till even lithium. And from these two periods, we actually get some information about the number of baryons we have in comparison to the photons. So the ratio between the baryon density to the photons is rather small, but this number is very important because that's how we have all the galaxies, everything from this leftover of baryons. And the impressive measurements is from these two periods. It's actually, I think the measurement from these two periods are in agreement, and the precision of the measurement is about a percent level, I think, the precision. And but we have no idea what happens before. But as we go up in the temperature, so we expect to have, so basically the plasma is hot enough to pair produce the protons and antiprotons. So we expect to have a lot of them. But since we believe a baryon number is conserved, so this difference should be the same. Just that today we only have of them annihilate, so we are left with baryon. So I use this capital letter to say that we have asymmetry. We have slightly more baryons than antibaryons. So just a side comment. So we could have assumed that there's a slightly more baryons than antibaryons in the beginning, but this explanation becomes very unappealing due to the requirement of a period of exponential expansion of the universe. So whatever you put in, so basically the universe you start as a blank slate after the so-called cosmic inflation. So this is the outline of my talk. So first I will go through the ingredients of baryogenesis. So this will be then I'll talk about the relation between the symmetries and the baryon asymmetry. Then I'll go to the main topics of the talk, which is to relate the baryon symmetry of our universe to another new sector through the so-called spiral process. So I will explain a bit what it is, and I will give an example, a model. So the ingredients for baryogenesis. So the first ingredient is we need baryon number violations. And in the standard model, this is actually there. So we believe that when the plasma temperature is above about 100 GeV, so this kind of process which violate both baryon and lepton numbers is actually very fast and happens all the time. So that means that if the universe is hot enough, so we have the first ingredient. And the second ingredient is also in the standard model of particle physics. So since a weak force only coupled to left-handed fermions, so the parity is violated. And then we have 3 generations of quarks. So that means that there's one phase that we cannot remove. So this phase result in a CP violation. And then the final ingredient is we cannot be in thermal equilibrium. So we need to be, because in thermal equilibrium, we have the same distribution for baryons and antibaryons, phase space distributions. Then we have the same number density for both. So in the standard model plus the cosmological model we have, so there are two possibilities. The first one is if we during the first phase transition in the particle physics model. So we believe that the particle physics gone through electroweak phase transitions. So the Higgs from being the wave of Higgs to be 0, and then from being 0 to non-zero value. And then the second one is also what we observe. We observe that the universe is expanding. So if there's some interactions which is slower than the expansion rate, then we know that this interaction is out of equilibrium. And then so basically these two ingredients, so it turns out that the CP relation or C and CP relation is suppressed due to we have the quark is too light compared to this temperature scale that we require to have a baryon number relation. And then the second one is due to the in order to have a first order phase transitions, we need Higgs to be light enough. And since we have discovered the Higgs with a mass much higher than this value, we know that this is not working. So in this talk, I will focus on having new source of CP relation and making use of the cosmic expansion for the out of equilibrium conditions. And I also consider the temperature above 100 GeV such that the baryon number is also related. So the symmetries, by symmetries, I mean the U1 symmetries, which you can think of the charges. So if there's a U1, like the electromagnetism, you have a conserved electric charge. So in the standard model, if you look at the Lagrangian of the Yukawa interactions, it seems like we have the so-called baryon number conservation and the lepton number conservations, besides and also the hypercharge conservation. But if you take into account of quantum effect, this is first pointed out by we have this operator which actually result in these interactions at high temperature. These kind of interactions. This operator actually violates both baryon and lepton number, but they conserve these 3 linear combinations. So we have actually, okay, alpha is 3 flavors of the leptons. So we have 3 and we have 1. So these are all conserved. But these two are very different because this is a gauge symmetry. So in principle, you have to be exactly conserved, but this can be broken, right? And then in the expanding universe, if we compare the interaction rates to the Hubble rate, so actually there are more these U1 symmetries which can arise. So you can imagine some interactions can become slower than the expansion rate as we go up in the temperature, because the expansion rate goes as a temperature. For example, in the radiation dominated universe, so it increases as a temperature square. So if we go up higher and higher, so it expands faster and faster. So at some point, some interactions might go out of equilibrium. So these are the different temperature threshold below which, above which we gain effective U1. So just to highlight, for example, below this temperature, the operator that I showed you before, it gets into thermal equilibrium. So that means the baryon number is violated below about 10 to the 12 GeV. If we go above, then baryon number is a good symmetry. And then all this label basically just means that, for example, this is mediated by the tau Yukawa coupling. So above this, the interaction mediated by tau Yukawa is not in thermal equilibrium. So this is a good symmetry. And so on. So if we keep going down, and then eventually, because electron has the smallest mass or smallest Yukawa coupling, so that's why this process get into equilibrium the last. So below this temperature, the only effective symmetry of the standard model is this 4. But if we go up higher and higher in temperature, so we gain more and more U1s. And so the final, as we know today, we don't observe proton decay, so there's no baryon number violations. So if we go below this temperature, so then the baryon number violation is again suppressed. Because to have baryon number violation, we have to go through tunneling process. So this is pointed out by 2. So then this again is baryon number is again restored to be a very good symmetry. So all this, since baryon number is not a conserved charge below 10 to the 12 GeV, so we can actually express baryon number in terms of other linear combination of the conserved charges. So just for example, to make it simple, if we consider temperature below 10 to the 4, so the only conserved charges are the 3B minus. So here I have taken the sum and the hypercharge. So you can see the baryon number is explicitly dependent on the conserved charges of the system. And so one comment is that since if the hypercharge is not broken, it's exact, so this is always 0. But then you can violate B minus L by introducing some new physics. The famous example is if you're introducing the type 1 seesaw for neutrino mass, so you can break this B minus L. And one interesting scenario arises if B minus L is violated, above this temperature. So in this case, what I mean is if just very similar to the baryon number violation in the standard model, if you introduce a source of B minus L violation, which is also in thermal equilibrium, then B minus L is not a conserved charge, but similar to baryon number, you can express it as a linear combination of other conserved charges. So here I said that you have to be above 10 to the 4 because above 10 to the 4 we have a lot of new conserved charges, right? So that means if we can introduce a new physics which generate, this new physics has to violate CP and generate a non-zero charges at some moment. So we can also induce a non-zero B minus L. Then when the universe cools down below this temperature, we have this relation. So because B minus L will be again a conserved number. Yeah. So basically, we have to assume that this B minus L violation interaction have to shut off at some point. Yeah. In the standard model, what we call Svaran process is due to the non-trivial vacuum of the non-abelian gauge theory, which is basically the weak interactions and the strong interactions. So basically, this is the operator we have seen before. So at high temperature, this operator will be in equilibrium. So similarly, for the strong sector, we have this operator. But this operator, they do not violate baryon number nor laptop number because here involve the conjugate of the quarks. So if you count the quarks number, the sum is 0. But they violate the so-called chiral symmetry. So the symmetry between left and right. These are left-handed quarks. These are the right-handed quarks. So in general, this is just to mention that you can write down this kind of operator for any U1x which is has the so-called ABJ anomaly or mixed anomaly with the non-abelian gauge theory. So as long as this coefficient is not 0, and then you can construct this operator. So each of the field which transform non-trivial under this SU and they carry the U1x charge, so they will comes in this operator. So if we introduce new physics, so we expect to have some new U1, if we have more degree of freedom. So one famous example is Petrie-Quinn symmetry. So which is what people use to solve the so-called a strong CP problem, why there's no CP violation in the strong sector. So by construction, if you introduce new degree of freedom, we require this new U1 to be anomalous. That means this coefficient is not 0. And similarly for the SU2, this spheron interaction, so we can introduce some new degree of freedom, which result in non-zero this anomaly with the SU2 gauge group. So now we can construct new conserved charges. No? Because we have to find out a new linear combination which is exactly conserved by the operator or these interactions that we have. So one is if we introduce a new page, this anomaly, but we can figure out a linear combination with this is the chiral symmetry of the up quarks. I choose as an up quark. So if we choose this linear combination, this will be exactly conserved, but they will be broken by the Yukawa, the up quark Yukawa interactions. I mean, this is a good symmetry or conserved charges down until this temperature T to the 6 GeV. But the other possibility, if we can actually construct this, because we know B and L are both anomalous under the weak interactions. Since X, U1X is this new charge is also anomalous, we can find a combination in which this is exactly conserved. In the standard model, these charges will be exactly conserved. So the conclusion is, okay, at least for now, is we can actually generate non-zero charges if we in the model by by generating some zero charges in these new charges, and then we will induce a non-zero baryon number. But there are some complications because once this new degree of freedom that we introduce, they actually have to carry the color charges or the weak charges, because otherwise you won't have the anomaly. So that means this new degree of freedom from experimental constraints, they cannot be very light. For example, the new particles which carry the color, or even the weak charges. So let's say their mass has to be TV, so such that we haven't seen them. So this, if we introduce the mass term for them, so this mass term actually explicitly breaks the what I call Porter charges that I introduced before. So if you make an estimation, you put the mass at the scale of TV, you figure out that if temperature is below 10 to the 8, so all these charges are, again, they are not a good symmetry. So that means we cannot use them, because that means they won't be there. No? We cannot use them for biogenesis. So one idea is what I mentioned in the beginning. So if we introduce the B minus L violating sources above such temperature, so okay, one example is let's say because neutrino mass in the standard model is 0, so one can obtain Majorana neutrino mass by introducing effective operator at dimension 5, the Weinberg operator. So if you look at this operator and you estimate when this operator will be in thermal equilibrium, okay, just putting in the neutrino mass indicated by the experiment, which has to be around 0.1 eV or lighter. So we have that above this 10 to the 11 GeV. So this process will be in thermal equilibrium. Or we have a B minus L violating sources, which is in thermal equilibrium. That means you can make use of this as sources of B minus L violation. So then this temperature, we can slowly generate charges, and then we induce a non-zero B minus L charges. So you see that below this temperature, this B minus L sources is shut off. That means B minus L will become conserved. You have a conserved number which is not 0. So you have the usual relation between the baryon and the B minus L. So in the last couple of, okay, 1 minute, okay, I will show the model. So the model is motivated by this to solve the strong CPU problem, the so-called KSVZ. So this model is very simple. You just introduce a pair of colored quarks, no, the right-handed and left-handed, and you couple them to a scalar, which is not charged under the standard model. But in this case, in order to have the biogenesis, I introduce, instead of 1, I introduce 2, this scalar. Okay, then just comment this tooth operator, they get modified due to these new colored fermions. So this is explicit the anomaly free charges. Okay, this is actually shouldn't, okay, no, this is fine. This is the charge carried by the scalar. So after this U1 HA queen is broken, so basically these new quarks will have a mass which is supposed to be much heavier than TeV. And then we have these interactions. So from these interactions, we can actually have a CPU relation, and we can generate a non-zero charges in this so-called PQ bar. So you can have this interaction. So so assuming that this wave is at 10 to the 11 when this PQ symmetry breaking happens. So then at this point, we also have, if we make use of the so-called Weinberg operator that I mentioned earlier, we have the B minus L variating sources. So putting all this together, we can actually explain this baryon symmetry. Okay, I'll leave my summary here since I'm out of time. So so I think I'll just highlight the last point because so these Saran porters, they act both ways. So you can, so the what I mentioned is that you induce a baryon asymmetry in the standard model sector, but first generating an asymmetry in the new sector. But of course, there can be the other way around. So you generate asymmetry in the baryon sector, probably you can induce also asymmetry in the new sector. So okay.
Time for 2 weeks or 1. Sorry, so then I will ask. So the transition is what order?
Here I did not make use of this phase transition. So here I think it's yeah, this breaking, yeah, it can be first or second, not doesn't matter. Yeah. If it involves the difference in the vacuum, then you get some dilution. Yeah, probably. Yeah, but for at least for this mechanism, we are just thinking after phase transition, then yeah, this decay happens. So it can be much below the phase transition, this decay. Yeah.
Yeah, yeah. About CP.
So thanks to the organizers for the opportunity to be here. I'll be speaking about astroparticle in general, but in this context of multi-messenger, as we learned in the previous presentations. In the context of multi-messenger astronomy, as we learned in the previous talks, the universe is very generous with us, sending many messages of different types of particles, radiations, and waves, but not only from a very wide range of energy. I made this scale, putting here basically everything that we have in nature. You can choose here your phenomena that you study, and you are going to find a place in this plot. Having energy, frequency, temperature, mass, or wavelengths that grows as an inverse of energy. So this scale goes down. This axis grows down. But I'm going to use these scales in the next slides just to remember us how the universe looks like in different wavelengths, seeing how information we have. And it's up to us to put all this data together and make a picture that makes sense out of the universe. Up to X-rays, we have what usually we call traditional astronomy. And then we have a transition, very didactically here shown from low energy to high energy, because up to this, the processes are thermal, so it can be explained by a black body radiation based on the temperature of the object that makes this radiation. But if you go up in energy, that cannot be explained anymore by thermal radiation. It's a different phenomena, a different acceleration process that gives energy to charged particles that are then converted to radiation. This is the case I read for high energy gamma rays, shown here in this plot of energies around above 10 to the 8 electron volt, corresponding wavelength of 10 to the minus 14 meters are read. As we learned recently from neutrinos, these are the extragalactic neutrino source that we know of energies above 10 to 12 electron volts. Charged particles that are scrambled in direction by magnetic fields above 10 to the 15 electron volt, or the highest energy map we have of the universe with energy above 10 to the 19 electron volt and wavelengths of corresponding wavelengths of 10 to the minus 25 of the meter, or at a very high in this energy scale. Just to be complete, we also have gravitational waves, as we saw many times this afternoon. And to summarize this, I'm going to highlight the energy ranges that I studied, because I studied, of course, but not only, also because they are very unique in the sense that they are the highest energy radiation we have access in nature, so that are TeV gamma rays, and the highest energy particles we have access in the universe, cosmic rays of above 10 to the 18 electron volt. If we plotted here the human-made machines to make radiation and particles, we would have a maximum energy orders of magnitude below of the ones we get from extraterrestrial sources. The observatories we participate that study these particles and radiations are the Pierre-Roger Observatory and the CTA telescope, the CTA Cherenkov Telescope Array. I'm not going to speak about the Pierre-Roger Observatory because we have seen many presentations, I believe. So I'm going to speak about this observatory that is being built and it's going to produce data in the next years. So CTA is an effort being put together for more than 2 decades already by more than 1,000 people. It's going to be the first open gamma ray observatory in the sense that the community, the international community, is going to be able to apply for data. All gamma ray observatories so far on ground, they do not have open time. They are observatories that are run by a consortium. It's going to improve our quality by an order of magnitude in basically everything, in sensitivity, in angular resolution. I'm going to show the plots. It's the missing probe of the extreme universe in the sense that we are going to probe the highest energetic phenomena in the universe, and is being built right now. This movie is shown for publicity. It was done by publicity, but illustrates very well the technique used by CTA. So these objects produce these gamma rays somewhere in the galaxy or outside. They come straight to Earth because they are not deviate. They interact in the atmosphere, producing this object called extensive air shower. Lots of particles, mainly electrons, are produced. And these electrons are ultra-relativistic, making a Cherenkov flash of light that can be detected by very sensitive instruments that are the Cherenkov telescopes. They have a very large mirror collectors shown here. So this is 24 meters, and a sensitive camera here that transform that into a signal. CTA is going to have more than 70 telescopes that are going to run in 2 sites to have a full sky coverage. These telescopes are going to measure simultaneously the same extensive air shower. So they measure the same object, the atmosphere. They make a movie of the development of this cascade, and the data analysis transform these images into the direction, energy, and type of the particle that arrive. This is how CTA is going to look like. It's going to be certainly a Hollywood image, seeing all these telescopes moving together. There are 3 types of telescopes. The large one with 24 meters diameter, this medium size with these ones 12 meters diameter, and the small telescopes with 4 meters diameter. They are very creatively called the small size, the medium size, then large size, the telescopes on CTA. So 2 sites, La Palma, Chile, so in the Canarian Islands, and here in Chile, with this very beautiful sky, as you all know. But I'm going to jump the final part of the movie because it's more for publicity. And I'm going to go a little bit more into the details of the science. CTA wants to improve the sensitivity in 1 order of magnitude, widen the energy range seen by only 1 observatory. So it's going to cover from 20 GeV to 300 TeV. There is no instrument nowadays that can cover this energy range. That's important to avoid systematics between different instruments. Increase the field of view, improve the angular resolution to something around 1 to 3 arc minutes, and have flexibility in operation, meaning that you can point all telescopes to one direction, make a very deep field observation of one source. You can place a telescope next to the other and make a scan for a large area of the sky. These are the telescopes. This is the first telescope on site running. So the first LST telescope in La Palma is taking data already and publishing papers. This is a prototype of the medium-sized telescope that was built in Berlin only to test the instrumentation. You cannot do science astronomy in Berlin. And this is the small-sized telescopes that we did not build 1 prototype yet, that because they're going to be built direct in the site. So the sites are not going to be the same. The northern side and the southern side have different types of telescopes in different numbers, because in the southern side you want to look at the galaxy, so you want to cover a different range of energy. The different types of telescopes are needed to cover this wide energy range. So the site in the north has more small-sized telescopes. The south, the site in the north does not have small-sized telescopes. Only medium and large size. So this is the consortium of more than 1,000 people, scientists and engineers building the observatory. And we are part of this group for more than a decade now. We have developed this structure here shown in gray of the medium-sized telescope here in Brazil. The design was done here, approved by the international consortium. We did 2 prototypes that were installed in the telescopes in Berlin. This is one of them, shown in gray here. And it was tested, it was approved, and we are now responsible for delivering 23 of these mechanical structures for all the medium-sized telescopes. This is the smallest part of this structure, the part here of this point here, being welded in a company in São José dos Campos, here in São Paulo. During the development, we were challenged by the design of the position of the camera. This is an instrument that wants to make an image. It weighs 2.5 tons and has 16 meters of arm. But it cannot deform by the weight of the structure. It cannot deform while it's moving. It cannot vibrate when you have wind. Everything has to be very well controlled. So there is a positioning mechanism here that moves 2.5 tons and keep this in position to make an image. We wanted to buy this position device to install it, but we could not find because the precision is not compatible with the weight. You have, of course, for those instruments, very precise adjustments, but none of them can hold 2.5 tons. So we had to design that, and the design is patented by the University of São Paulo, the University of Federal of ABC, and the company Orbital that developed this system. We have budget approved to construct 10 of these structures, and we still need to find for the rest for the 23 structures. So if you have a couple of millions that you'd like to invest in a very nice scientific project, you can contact me. There are 3 slides in this presentation I would like you to remember. It would be my pleasure to know that if you remember, one of them is this, that we are participating in the design of these telescopes with innovation developed here in Brazil to install in the telescopes. CTA is going to have then a sensitivity 10 times better than the current instruments. This is the sensitivity, the lowest flux you can measure with your observatory as a function of energy. CTA is shown by the black and red points. The current instruments running the same technology are shown here, MAGIC, Verita, and HESS, and this is what we say CTA is going to be at least 10 times better. Then you have here the low energy instruments, satellites that are not really comparable, and you have also the wide field of view instruments that are also not really comparable because they don't have point precision like CTA will have. Same idea here in this plot with the same instruments shown, CTA shown by the same colors, but here you have angular resolution as a function of energy. And again, this is from 5 to 10 times better than the current instrumentation. All of that is published in a book with more than 300 pages that you can access here. It's called Science with the Cherenkov Telescope Array that was produced by the CTA Consortium. And I challenge you to read this book and not find your scientific interest in it. CTA is going to open a new window in the universe in the sense of the number of sources. This is an estimation of this is what has been detected of TV gamma ray sources as a function of the years. So the number as a function of the years. The histogram and the integral of the histogram shown in red. The integral you can read here. And you can see that every new generation of instrument that started to run, you have a big rise in the number of sources detected. So HESS, MAGIC, and Verita started to operate in 2005. Then you have this large increase in the number of sources. Then HAWK, another increase. Then LIASSO recently, the last 2 years, measuring the very good science. And then you reach a little bit more, 270 sources since last time I checked the catalogs. CTA is going to bring this number to more than 1,000 TV sources in the first 10 years of observation. So you're going to multiply by a number of 4 the number of sources seen in the first operation. These are the key science projects, the CTA Consortium. As I said, I challenge you to read these and not find your interest here. We have 11 key science projects that are going to be done with 40% of the observational time of the first 10 years, which are going to be used by this consortium. I'm going to highlight here two subjects of these key science projects. One is the Large Magellanic Cloud, very unique galaxy, very nearby, that we know the distance very well, has a very high star formation rate compared to the Milky Way, and it's viewed face on. So it's a very laboratory for several science cases. It has this famous supernova remnant, it's in there, and has lots of structure. The current detection of gamma rays from the LMC is these 2 points. But we know there is a very detailed structure that might produce high energetic particles and gamma rays. What we did recently was a simulation of what can be expected to produce TeV gamma rays in the Large Magellanic Cloud. This is a very nice paper that was done by the consortium even before CTA has data, because this is legacy product for anybody that wants to study the LMC. And the second slide I would like you to remember, to know that you remember, is this one. This is what we know now from the LMC in the TeV sky, and this is how CTA is going to see it. So we are going really to start to probe details and see where the radiation comes from, which shocks can produce and which cannot. This is a simulation, not data. And the second point I would like to spend the last minutes is more on the side of fundamental physics, not on the side of astrophysics, which is using the propagation of these gamma rays to study the Lorentz invariance violation. These particles, they are interacting with the background photons of the universe. Gamma rays are interacting. And in each of these interactions, if you have a very tiny break of the Lorentz invariance, can accumulate the effect. And by the accumulation of the effect, you can probe very high scales of energy. You can probe the Planck scale without having one interaction in the Planck scale, because you accumulate the effect. And this is exactly the best scenario to do that, because you have the highest energetic radiation you know in nature and the largest distance you know in nature. So if you want an effect to accumulate, you have to go for astroparticles. We have been doing that. This can be summarized in a transparency of the universe for a photon of a given energy emitted at a given distance and facing a given background, so given photon background. You have the distance, you have the target, and you have the interactions here. Each one of these interactions you can do by assuming Lorentz invariance or assuming Lorentz invariance violation. In our case, I'm going to skip that. In our case, we have been testing the relativity only in this energy scale where we can do tests on Earth. So we know the special relativity works, but we know it works only where we can do the experiments. We cannot probe the relativity in the highest energies exactly where it is expected maybe to fail. So, as you know, the tries to unify the forces, as we saw in the previous presentations. One of the promising hypotheses is that if you allow the Lorentz invariance violation at the highest energies, it becomes a bit easier to quantify gravity if you don't. So one of the challenges is to keep Lorentz invariance and quantize gravity together. We do it only by extending the energy dispersion relation. So we add terms here, and then you have a perturbative approach of probing the Lorentz invariance violation, and you look for possible values of these delta 1, delta 2 that are different from 0. If you can detect it, you are going to detect the Lorentz invariance violation. But if you cannot detect, you set limits on the energy that could happen. And in the case of, so In the case of pair production, for instance, so you have one high energetic photon interacting with another photon from the background of low energy, you produce a pair. In the case of pair production, the mean pass function of energy changes in this way if you allow break Lorentz invariance. The standard Lorentz invariance allow breaks, the mean pass changes a lot, meaning the universe becomes much more transparent to high energetic radiation, the highest energies. Taking this effect into account in the propagation, we have been using current data to set limits. These are papers our group has been doing on setting limits on the Lorentz invariance violation. So if you add a break, the flux of photons increase, and there is a point that you cannot add more break because you would overshoot the data, so you cannot have this value of break. But we have been doing predictions of how CTA to see that. This is an energy flux as a function of energy, and there is a very unique feature that only CTA can measure, which is the recover of the spectrum. If the break happens at the highest energies, the universe becomes more transparent above a given energy. And because it becomes more transparent, a flux, an intrinsic flux that is cutting is going to recover because the universe is becoming more transparent above that energy. So this feature of a spectrum that is cutting down and recovering is a unique feature in Lorentz invariance violation. And this is the sensitivity of CTA, for instance, comparing to the current instruments. The current instruments could not see the recover, but CTA will be able to see it. Just to finish, the slide cannot move anymore. So I'm sure this is the chair that did somehow. He hacked my computer and stopped it to work because I'm already without time. Thank you very much.
One chair, superpower there.
Yeah.
One question.
I don't get Google Maps, they didn't find it. How can I find it?
It is the site. I think it's not in Google Maps. Yeah, it's inside the ESO site. So it's where ESO. If you look ESO, you find it. It's inside the ESO site. Yes. Yeah, of course, of course. Everything stopped, Ivone. I don't remember where is the bump? I'll show you and then we discuss. Yeah.
Did I miss this time the time scale for the data?
First data in 2 years. First, well, the data is coming from one telescope, but the largest running observatory now has 5 telescopes, which is HESS. So CTA becomes larger than HESS in at least 2. In 2 years, we are going to be the best observatory in gamma ray. Thank you.
Okay. So I will talk today about search for light, dark matter, and liquid orbital targets. But the main question here is related to dark matter direct detection. As we all know, the best limits for probing dark matter comes from noble liquid targets. Either liquid xenon has the best sensitivity for this. So, however, these detectors are optimized to detect dark matter above 10 GeV. So the question here is, can these experiments like liquid that has liquid xenon or liquid argon probe light dark matter? So I'm talking about liquid argon not only because I'm a member of the Dark Side collaboration, but also because we were the first collaboration to show how you can go to light mass in liquid noble gases. So just there was a recap. Dark Side started with a tiny 10 kilograms of liquid argon detector just to show some detector feasibilities, but our first detector that has good science results is Dark Side 50, which has 50 kilograms of liquid argon. And we have not only results related to direct detection of dark matter, but a whole bunch of other interesting effects like Migdal effect and this low mass probe that may show that you can actually do this with these kinds of detectors. We are now building the Dark Side 20K, so we're jumping from 50 kilos of liquid argon to 20 tons of liquid argon. So that's a big jump, and we have to understand a lot of stuff. So in between this, one of the things we have to understand is, if we want to probe light dark matter, is what is the nuclear recoil behavior at very low energies. And for this, we have this tiny detector, which is called recoil directionality. I'll mention the name, which is a very small TPC, time projector sampler. So it's the same detector that will be used in this huge Dark Side 20K, which is 20 tons, but where we shine neutrons on it. And the reason is you expect that neutrons will interact in your detector in exactly the same way as dark matter will. So we use this small detector, shining it with neutrons, in order to probe some crucial parameters that will be used later on the big detector if we want to probe light dark matter. So just as a reminder, the Dark Side detector, as well as the xenon experiments, most of them are double phase. And that means you have liquid argon and a little pocket of gas, argon in a gas form. And the principle here is that your dark matter will come, interact with the argon nucleus, and there will be prompt scintillator light emitted from this interaction. And that's what we call our S1 signal. And you have an electric field surrounding your detector. And for this reason, the ionized electrons will merge to the top, and then you have a stronger electric field, here, and this stronger field makes the electron accelerate and produce electroluminescence, and this is what we call our S2 signal. So the great advantage of argon in relation to xenon is what we call pool shape discrimination. And that means that when you look at your signal, your analysis, so these are counts and a shape that the signal will produce in these photomultipliers here, or in the silicon PMs that will be used by Dark Side, the electron recoil shape is very different from the nuclear recoil. By electron recoil, I mean that your particle that's coming in interacts with the electron of the atom. And the nuclear recoils is when the particle interacts with the nucleus of your atom. And here you have most of the background. So these are backgrounds that comes from various sources, and it's either produced by electron interacting with the electron of the atom or a gamma. Sorry? Yes, yes. And these are two real signals. And you can see that the electron recoil is much broader than the nuclear recoil. So the pulse-shape discriminator in argon mainly uses this fact, and we integrate the fraction of your signal within a small time window. So this is time. This is ADC counts, which comes from your electronics. And most of the nuclear recoil is a large fraction of your signal, while the electron recoil for dark side 50, this time interval was 90 nanoseconds. You can see that most of the electron recoils will have a small fraction in this interval. So you can mainly reject all the electron recoils, which is the main background, and you just use the nuclear recoils. So this is pulse-shape discrimination, and this, you cannot use this in xenon. So this is the strong feature of using argon. So here is the current exclusion region. Unfortunately, I didn't find dark matter so far. And this hashed line here, region here is from LZ, which uses liquid xenon. And it has the best limits in dark matter so far. You can see this is the cross-section, spin-independent cross-sections between dark matter and a nucleon. And this is the mass of your dark matter. So you can see that we already reached 10 to the minus 47 here at 0.1 TeV. So this is 100 GeV. You can exclusion of very low cross sections. So due to this fact that we didn't find dark matter yet, although we still have many decades in cross section to go, so these solid lines and even these lines here, they are all future experiments. So we'll go from here and we'll probe what you would say, where dark matter is expected in the next generations of direct detection. In orange here, we have many models where they expect to have a signal. So, but the question here is, all these detectors, both in xenon and argon, they were optimized to measure dark matter above 10 GeV. As you can see, it goes up here, the constraints, and that's because the efficiency of these detectors is not good in this region. On the other side, you have, due to the fact that dark matter wasn't found yet, and due to the fact that you have a lot of motivation from the theoretical side, where you have, both asymmetric dark matter and dark sectors have many candidates that will have mass less than 10 GeV. The question is, can these detectors do a good job in this region too? And one important thing is that everything I told you about pulse-shape discrimination is only related to the S1 signal, so the prompt signal. So the problem here when you go to lower energies is that you cannot use the S1 signal because the energy in your detector, it's too small to be detected. So you have to do a S2 only analysis. So mainly you have to give up pulse-shape discrimination and argon. So mainly we ask the question, is this possible? Can we use these detectors to probe this region here? And that was some work we did in USP. So the conception, the idea of this analysis and the development, everything we done in our group in USP. And what we did is, I'm not going to get into details, but mainly we use data that's not good for dark matter probe. We use the detector when it was dirty. So our purification system, which we call getter, was off. And with this, you would have that in the argon, the electron, a single electron will be held by impurities and then released. So we could use this single electron to understand how many photoelectrons in your photomultiplier you get for one electron. So this is a calibration that you cannot do, we could not do using just the data that we use for dark matter search. So this is data that's discarded because it's not good for dark matter. So we calibrated our the number of photoelectrons produced by a single electron, and then we use another data that's not good for dark matter. That's the contamination of argon 37 that comes into the argon when we fly our argon from the US to Italy, because the argon is got from underground in the US and we have to fly it to Italy. So argon 37 has a 30-day lifetime, decay time. And when it decays, it produces two peaks, one on the L and the other on the K shell. And we know the energy of these peaks. So we could look into our data here when, you know, we're still contaminated by argon, and then it will decay, will not be a problem for us. But we don't use this data for dark matter probes. So we use this, and we use these two known peaks to calibrate the energy as a function. So how many we know the number of electrons here. From the previous slides, we know the number of photoelectrons in your photomultiplier, and then we can pin down the relation between the energy and the number of the photoelectrons. So this was somehow a different kind of analysis, and that made possible to go to low energies. So here we have the mass of your dark matter. This is 10 GeV and lower, and this is the spin-independent cross-section. So this red curves here comes from dark side. As you can see, if you remember, dark side here has 50 kilos of liquid argon, and xenon has 1 ton. And we have the best results. And the only reason is because somehow we came up with this analysis that's completely different. And from here, we showed that you can do this, and suddenly there's a whole opening and looking for low, light dark matter with noble liquid, both for argon and for xenon. So this was the original analysis. Now we updated it with more data. But the question now is, you see here we have a region where our results will fall. And the reason why it's not a single line is because we don't know exactly the ionization yield in this low mass region. So what is the ionization yield? Ionization yield is the fraction of the energy that's transferred from the dark matter to your detector that's actually detected. Because in the exchange, when the dark matter transfers energy to your detector, a part of this energy is lost. So your measurement is quenched. You measured what you can, but some of the energy was lost to heat. So you need to understand what is the fraction that you actually measure to be able to pin down the dark matter energy. So we call this ionization yield, or the opposite would be the quenching of the energy that's transferred to. So this ambiguity here is due to not knowing the ionization yield at very, very low energies in liquid argon. So, oh, I went to the wrong direction. So for this, we're using this small detector that I mentioned, the red recoil directionality experiment. It is a small TPC, 5 per 5 per 6 centimeters. It's only 185 grams of argon, and its main goals are test if liquid argon can pin down the direction of the dark matter wind, and our results are here. I won't talk about this today. Then this low recoil energy measurement, that's what I'm talking about now. And also to test, instead of having photomultipliers, we have silicon photomultipliers that will be used by dark side 20K. So we're testing this for dark side 20K. So mainly this is it's a miniature of the dark side 20K detector. So I will concentrate here in the efforts to measure light dark matter, which is this low recoil energy measurement. So we showed also, this was work done at USP, we showed that the, oops. Yeah, well, I missed one slide. But anyway, we showed that the setup to measure the directionality of dark matter effort in red used the beam in Catania. So what we showed is that their beam was very good for higher energy probes, but if we want to do the low energy modes, that beam, it's lithium beam, wouldn't be good. So we showed that you can use two sources of neutrons in order to measure this crucial parameter, which is the ionization yield. And that's using either radioactive sources, or which we chose to be a California sources, or maybe ANT to use a neutron generator. So we ran the experiment in this mode already, and we're buying the neutron generator, which will be help PESP, which will be commissioned at USP and then taken to LNS, to Catania, in order to use the TPC. So we can then go down to 0.5 keV in probing the ionization yield. So this is just the general idea. So this will be both for the source as well for the neutron generator. Many of you have the source here, and it will shine neutrons here. And the Californian source, it emits gammas at the same time. So you have a tagger here that will tag these gammas, and you can then measure the time of flight of your neutron all the way to your detector. This is the neutron detector, which consists of plastic scintillator. So it will interact in the TPC, scatter, and be detected here. So we can tag from the time of flight, we can determine the neutron energy. And then by using the TPC vertex and the place where it hits the plastic scintillator, you can determine the recoil energy. So this is actually a picture of the experiment itself. And as an example, if you have an angle here of 12 degrees, it will give you a 3 keV neutron recoil for 2.5 MeV neutrons. So the neutron recoil is just a two-body decay kinematics. I won't get into this. So this is, we ran from January 10th to March 16th last year. And this is the data we collected. And as you can see, we will have neutrons and gammas. So let's go slow here. So I said that we don't have the pulse shape discrimination on liquid argon. And what I'm showing here is a pulse shape discrimination. So that's a confusion, but this pulse shape discrimination is in the plastic scintillator, not in the TPC. So you can do pulse shape with the plastic scintillator. Of course, for dark side, you don't have the plastic scintillator. So we need to determine this parameter, then dark side can measure light dark matter because we are determining this parameter here. And we use the pulse shape discrimination in the plastic scintillator. So the radiative source will emit neutrons and gammas promptly. So these gammas are associated to these neutrons. And then you have a background of gammas that are from hitting the cryostat and so on. So you can see that our data is dominated by gammas. However, we have the capability of selecting the neutrons very well. So that's what we did. So this plot here gets, 820 neutrons from what I showed before, from 3200. In blue are the events that have S12 only in the TPC, and we have events that have S1 and S2, and these are mainly multiple scattering neutrons. And this matches very well our Monte Carlo. So we get the 75% of S2 that has S2 only, and with this we can determine the nuclear energy down to about 1 keV in the detector. And this means that I know the energy of the neutron that's getting in the TPC. Here I know the energy that I measured, so therefore I know the ionization yield. So just to finish, the next step is to use a neutron generator. The great advantage here is that we have a monoenergetic beam, so we don't need to reconstruct the energy of the neutron as we do for California source. And just going, since I have zero min, this is our setup to do some testing of the plastic scintillator. This is Nicholas, our postdoc. And one important point is that we don't have, so the neutron generator is a deuterium-deuterium interaction that will produce neutrons and helium-3. So to be able to do time of flight, we had to talk to this company which produces neutron guns to see if we can see helium-3. The importance of seeing helium-3 is to do time of flight. You measure the helium-3 and the neutron and the passive scintillator, you know the time of flight. So we're modifying what they have according to our needs. So we went to Adelphi at California, and this is the setup. Here's the neutron gun. So this is where we put a silicon detector to measure this helium-3. And so the helium-3 will come this way, the neutrons will come to this plastic scintillator. So the question is, before we buy such a thing, can we see the helium-3 peak? We can. So here's the answer. You can see the helium-3, and this in red is what our Monte Carlo. At the same time, they are also produced protons and pretions, which you can also see. So it was an effort that was successful, and we are now acquiring the neutron generator. So next steps, we have with red measured the response of liquid argon down to 1 to 2 keV in neutron recoils. Therefore, we can determine the ionization yield here. The neutron generator will be commissioning. It's arriving next month. And then once we get it here, we will send it after commissioning it and understanding, calibrating it. We'll send it to Italy so it can shine the TPC. So that's the near future for red. And we're also extending the California measurements with this funding here. And so red will measure the nuclear quenching down to half a single keV unit. This is crucial for light dark matter searches and direct detection. And the dark side low mass analysis will improve a factor of 50 in relation to dark side 50 if we have this measurement. Thank you.
Yeah, that's a good question. So nuclear recoil that the factory are nuclear recoil or the electric recoil?
Yes, so what we're interested in nuclear recoil because the interaction will, we also have work that's an electron interaction. That's a different thing. But here, yes, so we do have work, I didn't show here, it's listed when the dark matter has so low mass that it will interact with the electron. So we also, so it's maybe the same analysis that we did, but with the models, the models have a different curve. We can, yes, yes. Yes. Oh, no, it's testing, but this test was done right in the beginning. This is done already. So it's silicon PMs. Yes, it worked very well and it's much better.
So I think you answered that. So you're building this neutron center but show pictures of lab in the USP. So you have a permanent lab where this technology?
Yes, so we were offered a very nice lab at the Linear Acelerador in USP. And this picture of, not this picture here, this is actually the linear accelerator that has nothing to do with us. So our experiment is here. As you see, we put a source here. So here, and this is our electronics. So what we were doing here was testing the DAQ. So we will have, so this is part of a lab where we are now, but in the floor below, we have a whole space for us. Well, for now, this what we will do all these tests with the neutron generator and then send it to Catania. My idea is that we should use this space for neutrinos and dark matter, not searches because you don't have you're not underground, but to develop R&D for these kinds of experiments. We can talk.
So those of you who have received the invitation by email are welcome for speech upstairs. If you haven't received the invitation, you can hope that you come left over. No, after 7, yes.
Yeah, so.
But I thankful for the fact that it's our big, cover me.